And I just want to introduce myself. I'm Derek Alconis from Los Angeles County Fire Department, also a member of the Fireground Survival Group here with the IFF. We also have Steve Kerber of UL and Dan Majikowski of NIST. And we're going to spare you with all the details of our bios. If you want to learn more about especially these two guys, there's not much learned about me, but you can Google them. I'm sure a bunch of stuff will come up, so you can check that out. I wanted to start this off by sharing a story. And it even irritates me as I start to think about what I'm going to share with you right now. It was in 2012. I went to FDIC. And I was there attending some classes, excellent workshops. There was one that was being offered by Bobby Halton, and he had two prominent members of the fire service. And they were going to talk in a kind of, it was supposed to be like an intimate discussion at the firehouse. In fact, they had it on stage as if it were in the kitchen or the rec room of a firehouse. So it made you feel like you were there, you know, and I guess that was kind of the idea. I'm going to try to wander around with both sides so I can see you guys over here, right? So once in a while, and Marty's just going to have to do his wonders with the camera. Sorry about that, Marty. So anyway, I go in this huge room, and there seems to be thousands of people there. And they start to talk about different subjects that are, I don't know, they're prominent topics in the fire service. Current events, what's going on? And so I'm listening, and then they start to turn to the subject of structural fire behavior and some of the research that's being done by UL and NIST, and some of the stuff that had recently come out about ventilation and about how we need to be conscious of how we ventilate a structure. And perhaps we haven't been trained correctly, or we haven't been performing to the way that the research says we should perform. The two prominent members of the fire service, which you probably know, and I'm not going to mention their names, but they basically wanted to throw the research, roll it up in their hands, and throw it in the trash can. What they said appalled me as a career firefighter. They basically said, you know what these guys have dedicated their lives to do to improve the fire service, and what we do as firefighters, forget about it. Just do like we were taught to do, and as our grandfathers and our fathers had experienced, or the veteran firefighters have told you to do. Don't be concerned about the research. Well, that's sticking your head in the sand. If we're professional firefighters, then we have a responsibility to do the research, to make sure what we're doing is correct. It makes sense. In fact, retired General McCaffrey mentioned that in his talk. He said, true leaders know something. They're smart. He even said they read. We have to read. These reports are long. We understand that. Some of them are 500 pages long. It's going to be difficult for you to go through 500 pages. But they've got executive summaries that are about 10 pages. All you need to know is right there. So we're going to take you through several things here. I share that story because this slide right here, knowledge versus belief. Let's look at some of these things. They're posed as questions. Because some folks believe that if you vent, it actually cools. Dan mentioned this in his talk this morning. Is that really true? And you have to look at these. They're stated as questions because it should provoke some kind of thought in your mind. Does it really mean it's cooling if I ventilate a structure? I'm going to promote more cooling? No. Exterior fire attack is for defensive strategy only. That's not necessarily true, is it? Basement fire should be attacked from the top down. Exterior fire attack will push fire. I like that phrase, pushing fire. Because in wildland firefighting, where I come from in LA County, when I pull out, when I was an engine company captain, shoot, probably, during the course of the wildland season, you may go on 20 or so grass and wildland fires. And during that time, when we pulled our 1.5 inch out and we were charging up the hill and the grass was on fire and the wind was blowing at our back at around 15 to 20 miles an hour, you know what? In order to put the fire out, we put water on it. And it didn't push the fire up the hill to make it bigger. And we even brought helicopters in and dumped more water on the fire, and that put it out too. So it's kind of interesting. It does. Water puts out fire. It doesn't push it. Okay, exterior fire attack will hurt victims. This is another personal experience that I've had in working in some of the busier areas of LA County. One particular area, which I worked at for about 9 years, the residents were very aggressive if they had a fire inside their homes. And in fact, we would often see them with their garden hose going like this and putting the fire out as we arrive. And just the garden hose would do amazing things inside of a window. So was it hurting the victims inside? No, as we rushed in the front door, typically people were okay. They were getting out. It wasn't hurting us either. It wasn't pushing the fire in our direction. The best way to aid victims is vent the building and search before suppression. I'm not going to go through all of these in detail because we've got a lot to share, but think about those things. What do you know about these statements? And let's put some facts to it. Okay, so if you hear these statements, never ventilate, never go inside, always throw water from the outside, no. Never go over a basement fire, never vertically vent, or everything you did in the past was absolutely incorrect. And if someone's telling you that this is what the research is telling us, then you're either not reading it carefully or you're not listening carefully, because this is absolutely false. The research doesn't say any of these things. And so the discussions that we have in our firehouses, they get very emotional over this topic, and we all know that we've been there, we've experienced it firsthand. These are the kind of statements that are offered by folks. They're saying never go inside. They're crazy. They're saying we can't vertically ventilate. They're saying that, you know what, everything that the folks that came before us did was wrong. That's not the truth. The way firefighters were fought 30 years ago were due to what was burning 30 years ago. Times have changed. They're going to present those facts. All right, here's what we should be hearing or should be thinking. That we know from our experience in the Fireground that it's rare that there's an always or a never. You know, that's the Fireground is dynamic. It's always changing. Or the next statement, that's why we do that. It's glad to know that I've been doing something right. That's why we do it. That could work for my department if we train on it. Say that statement over to yourself and you say, shoot, yeah, I think if I applied that, that would work in our department. I can use this information to be more educated, aggressive, than ever to do these things, to put the fire out faster and more efficiently, to have less of a chance of getting hurt or killed, to preserve more property, and of course to reduce the chance of victims or ourselves being killed or injured. And you know, like that statement says right there, the science of firefighting is not that complicated. It's about the fire triangle, and they're going to demonstrate that for us. But as firefighters or structural firefighters, we have not been trained in the subject of fire behavior very well. And this is just a snapshot of what's going on in the country, around the country. Now, some of you work in different states that may have or may require more fire behavior training. But here's just a snapshot. Firefighter 1, you've got 102 hours of total fire training. Some are more, some are less, we understand that. But only 3 hours of fire behavior training goes on within that 102 hours. How about Firefighter 2? You got 60 hours. There's no fire behavior training. And then as you progress up the ranks, there is no fire behavior training for structural firefighting. Now, for those of you who are wildland firefighters, that may be different. because you do have S190, which takes you 8 hours, S290, that's 16 hours, S390, that's 4 days, 5 days, and S490, that's another 5 days. So that's quite a bit of, of education as you make your way through the ranks in wildland firefighting. So we're going to have to invest. In fact, this is going to be addressed on the next Health and Safety IFF Firefighting Grant, AFG grant. They're going to dedicate some resources to developing a structural fire behavior course curriculum of some sort. And we just found this out earlier in the week. So that's exciting. Let's look at our experience. So if we don't get if we're not getting the information from our education, then obviously we're getting it from our experience. But if you look at this slide, and obviously it doesn't represent everybody in this room, however, you just take a snapshot of how many fires that we go on as in the United States, about 500,000 per year, okay? So in here you go, 10 million structure fires in 20 years, about 500,000 per year. A typical career, you may go on 10 good structure fires. Now some of you have been on maybe that in half the time. We understand that. But the point is you can't get a big mustache like that unless you've been on some structure fires, right? That's what that is. That's a mustache. That's not baleen from a whale. And you can't get your helmet like that unless you've really been in a lot of fires. But we're not getting a whole lot of fires out there. So we have to shore up that lack of experience with something else, which is education. And the scientists are providing the research to ensure that we're doing things correctly. So what has changed over the last several years in firefighting? Well, the expectations of the fire service definitely has changed. We go on a variety of different calls, and it's an all-hazard fire department now. Technology, the fire environment, fire service research, the pace of change is incredible. And we have to stay relevant. With all this new information coming out, we have to be able to read it, understand it, and implement it within each of our organizations, which is probably the most challenging, is these folks are getting the stuff out there, and it's well published, and it's easily accessed. The challenge is how do we implement it? And within today's presentation, you're going to see just one way on how you can implement it. All hazard, these are all the different expectations on a fire department. We know they're plentiful, but nonetheless, we're responsible for ensuring that our firefighters are well trained to be able to respond to these emergencies. These are just a snapshot of all the different things that are changing. You look at the turnout gear from past to present, the SCBAs, and the thermal imager, the nozzles, the blowers, the apparatus. Times are changing. Well, it would just make sense that we would have a better grasp on what is happening fire behaviorally inside of a structure fire. And luckily, we're living in a day and age where we have access to that information. We can repeat experiments over and over again in a laboratory to ensure we get the data that will inform us on how best to go about structure firefighting. So with that, we're going to go to Steve, and he's going to tell us a little bit about the research that UL is doing.
Thanks, Derek. All right, so we're going to start out really laying out the presentation objectives. What do we want you guys to get out of this? And I'm going to cover the first part of that, which is understanding the changing fire environment. Derek had mentioned it's not the same playing ground as it was when your fathers, grandfathers, great-grandfathers, depending on how many generations you have in the fire department, how it was different for them, how it's different for you today. Let's try and look at some of those things. Because ultimately, it's not, you're fighting a moving target. And we're going to talk about all the components that go into the complexity of that. Improve your understanding of fire dynamics. Weird word, fire behavior, fire dynamics. Really, fire dynamics is taking in everything that includes fire behavior, the structures that it's in, the materials it involves, all the physics behind what's going on. We're going to give you guys a better handle on that. Importance of size up and choosing tactics that fit the conditions. If you don't know what's going on, how do you know how to address the problem? And based on how the problem's changing, what are we seeing in the research as some tactical considerations to make you better today? Reevaluate your ventilation practices. In most cases, ventilation commonly gets overlooked because it's thought of, this is just the thing that makes things better. Well, when you have an environment starved for oxygen and you provide that oxygen, the difference between a good result of ventilation and a poor result of ventilation could be the difference between 10 seconds, 20 seconds, 30 seconds, a couple minutes. Do you understand that timeline? And how do we coordinate that timeline so you're most effective? Understand the collapse hazard. We've done a ton of research on basement fires, and we're going to get into that pretty in depth. Re-examine your suppression practices. Where you start your attack from is very important, and we're going to talk about the differences between what you see when you show up and what the potential output would be of the tactical choices you make as far as where the hose line goes. Provide you more information to teach your members. Dan and I and now Derek have websites where we're putting all our information up. The purpose here is for not us to travel around teaching this stuff. It's for you to take it back to your department and to implement it. We'll make sure that you have access to all this information. And make you think more and ask why. If we're really going to improve as a fire service, we need to continually ask why we're doing things. And unless we understand why we're doing them, we can't have the smart firefighters and fire officers on the fire ground making the quick changing decisions that need to be made based on what you see. If we're a bunch of robots that all we know is how, and all we know is our SOP, and we don't know how and when and why to deviate from that, or when to follow it, or how what our size up tells us dictates what we do, then we're in trouble. And I think we can get to that why, and we can be smarter firefighters. I want you to remember these things. There's a big difference between theory and tactics. We understand that. It's very complex on the fire ground. But we're going to try and bound that problem and give you information that you can apply, or more importantly, know what your plan A is, know when to go to a plan B, and things along those lines. Engineers don't have all the answers. I know that's hard to believe. We can't run every possible scenario that you're going to respond to. It's impossible. There's not enough money, there's not enough resources, there's not enough of Dan to be able to do that. However, as you'll see as we go through this, the reason we're picking the scenarios that we do working with the fire service is that we can begin to bound the problem. And if we know what happens on this end and on this end, we've got a pretty good idea what goes on in the middle. And if we start seeing the same trends over and over again, a lot of what we're going to present isn't from one test in a lab. We're up into the over 100, probably approaching 200 full-scale experiments, whether it's single-family houses, townhouses, full-scale stuff in our lab, acquired structures, stuff in cities, stuff in suburbs, big buildings, small buildings, high-rises, and everything else. The physics doesn't change, and we're beginning to put all those pieces together, and that's what we're sharing with you. There aren't enough fires to make you an expert. The one thing that we can do in research that you cannot do in the field is, all right, I'm going to show up. I've got this very simple 1,200 square foot ranch house on fire. I got fire in the AB corner. I'm showing up. I got smoke showing, lines going through the front door. Fire goes out. Was that the best way to do it? What if you would have vented opposite the hose line, or what if you would have cut a hole above where that fire was as you were moving in? Would that have been better? You'll never know. Because you're not going to that same 1,200 square foot ranch house with the same fire in the same spot to pick a second choice. You don't get a second choice. In research, we do. We can get 20 choices on the same fire. And we can say, well, I didn't want to vent the AB corner. Let's see what happens when I vent the CD corner. Or what happens if I VEIS the back bedroom while the hose line's going through the front door? What if I make a 4x8 hole instead of a 4x4 hole on this fire? You don't get to do those things. You go to very different fires. You could go to 10, 1,200 square foot ranch house fires, and if the fire's in a different spot in the house every time, you may get a different response from your tactics. How do you put those pieces together? Well, we can do it through education. We can do it through fire behavior knowledge. And now's a really good time. I think for a long time, all the fire training books had the how to do things. Here's how you force a door. Here's how you break a window. Here's what ventilation is. Here's what suppression is. Without a lot of details, because the information didn't exist. Well, fire dynamics research picked up on the fundamental side, so we understand how fire grows and spreads. Money became available through different sources to do research with the fire service. We took advantage of that, so we took the principles and we started to apply them at a full scale. And then we got a whole bunch of engagement from the fire service saying, we want to know these answers. So we started putting these three groups of people together, and really what you're seeing today is the results of that. So let's talk about today's fire environment. What's changed? The important piece here is it's not any one component. Houses are getting bigger, spaces are becoming more open, fuel loads are evolving, void spaces are changing, building materials are changing constantly, and new technologies are being integrated into your work environment every day. Any one of these could present a serious problem for you. The difference is they're all coming together at the same time, and they're all changing extremely rapidly. Can we understand how that impacts our operations? Well, ultimately, you put them together, and you start getting fires that are growing faster than they ever have, civilians with less time to get out than they've ever had, structures that are falling down around you quicker than ever, and hazards that you may have never even seen before that you need to be experts at because someone's calling you to deal with their problem. Let's look at all of them real quickly. Home size increased from about 1,600 square feet to 2,600 square feet over the last 40 years. Is your staffing of your department increased because the hazard's increasing? More than a quarter of the houses built in 2008 were greater than 3,000 square feet. Have you changed the complement of firefighters that you have responding to those incidents? In many cases, probably not. Open spaces. This one kind of goes hand in hand with the changing building materials. So what we used to have was dimensional lumber. You could only span so far with dimensional lumber. So now let's say the most you can have is a 16 or 18 foot span to make a room a certain size. Then we went ahead and we developed I-joists and trusses and things like that can span a whole lot longer. So now with the dimensional lumber, we need a whole bunch of bearing walls. Now you don't need those bearing walls. Now families enjoy open spaces. So now you have rooms inside houses that used to be confined and compartmented, which could compartment the fire and work in your advantage. And now all that compartmentation is being ripped out. Any one of you has probably removed a wall in your house or bought a house with an open floor plan because that's a popular thing these days. That's something that we want. It's going to change how that fire responds. Great rooms. You now have 15 to 20 foot ceilings in houses. You think the same fire development is going to happen in an 8-foot ceiling as it is in a 16-foot ceiling? Different things are happening before you get there. If you've got line of sight, that fire's got line of sight. If you now have a first floor of a house that's completely one compartment, your fire flow may be different than if you pull up and you've got a 12 by 12 front living room on fire or a small bedroom on fire. It's going to change how your water interacts with that problem. Evolving fuel loads, this is a big one. We're moving from a natural to a synthetic dominated environment. The potential energy in the fuel is very different. There's more there to be released, and this is where you're going to start hearing the term heat release rate. Because the speed at which that energy is able to be created is your problem. Temperature is just the end result. Temperature is because the energy got released. So if the temperature is 1,000 degrees it's going to be 1,000 degrees whether you're burning cotton or whether you're burning polyurethane foam. The question is, how quickly does it get to that point of flashover? How quickly does it get to the point where you're running out of oxygen to burn that it's going to get from your operations? So we've got a neat lab in Northbrook, Illinois at UL, 120 feet by 120 feet with essentially a large aircraft carrier deck as a ceiling that we can move all the way down to the 5-foot level or all the way up to 60 feet, and we can simulate different warehouse configurations. Well, when we're not running warehouse configurations, I've got a little playground. I can pretty much build anything. So we start out small. Here's a couple rooms side by side. Modern room, legacy room. Modern room is stuff that I went up the street and bought. Legacy room is I went on Craigslist and I tricked old ladies into selling me their old stuff that you can't find in the store anymore. You put those two things together, you get a very different fire scenario. So you can see on the left-hand side, there's your modern department store sponsored room. On the right-hand side, we did take the plastic off of Grandma's sofa, so you've got cotton-covered cotton batting in the furniture. It also has furniture that was actually made of solid wood. Good luck finding that today without paying a huge premium for it. The stuff in the modern room is all particle board. Kids' toys, modern room, all plastic. Legacy room, made of actual wood. Did we miss a video in there? Okay, so we're skipping the side-by-side room and we're going right to the side-by-side house because the side-by-side room is too boring. So what we did here is we did the same exact thing except we did it in two 1,200 square foot houses. So two houses side by side. The important things that we're looking for here, we light them both with a small match. We're looking for how long does it take for the fire to run out of oxygen, and then from when we give it air until when it goes to flashover, what is that time period? And that begins to give us our operational time frame that we have to work within to coordinate our attack. So you can see we're 5 minutes in. Your modern fuel, we're blacked out. We've got zero visibility in that entire house. We're beginning to run out of oxygen. Legacy room, you've got white wispy smoke. It's trying to grow. It's getting there. What we did is from the moment that fire began to run out of oxygen, we gave it 3 minutes, and then we went ahead and simulated fire department operations. The simulated operations are opening the front door at 8 minutes, opening the front window at 8 minutes and 15 seconds. Allow that fire to respond to the oxygen and see how long it takes to go to flashover. In this case, about 2 minutes, 15 seconds, we go to flashover. So you see 5 minutes to ventilation limited, another 2 minutes and 15 seconds from ventilation to flashover. So best case scenario, everything's sealed up, fire runs out of air, 3 minutes later you show up, you need to be putting water on that fire in that first 2 minutes to make sure that that fire does not go to flashover. Ideally, you want to do it in the first minute so that it never increases in size, it continues to decay. Legacy fuel. All right, now it's getting painful. We're at coming up on 18 minutes and you still have visibility in the fire room. You've got fire that's on one sofa trying to extend to the other sofa. We had some flames roll the ceiling, but it starts to run out of oxygen. Pretty much at the 20-21 minute mark is when the temperatures start to decrease. It starts to starve for oxygen. So at 24 minutes, we're going to go ahead and open it up. Front door, front window. See, we're finally starting to black out inside. We go ahead, we open it up. You can see the smoke lifts quite a bit. You get pretty good visibility all the way back into the kitchen area. Fire is still confined to one sofa and some carpet. It's going to extend to the second sofa. And we're waiting for enough energy to be released at the same time that the fire is starved for oxygen and has to burn to the openings, has to burn to the front door and burn to the front window in order to get air. Pretty soon you're going to see me and my lab tech have a conversation. Do you think it's going to go? I'm not sure. Do you think it's going to go? I'll go look. And it goes ahead and transitions because it finally got the front two chairs going. So what's our timeline? Well, it takes 4 times longer to begin to run out of air. Who's got response times where you can get the call, get to the scene, get a line off, and get it in operation in 20 minutes? I hope there's a lot of hands going up. That's reasonable, right? How many people can get the call, get out the door, and get water on the fire before the 5-minute mark? Not many. And if you got your hands up, it's because you're sitting on the rig, someone tweeted, couch is on fire, and you stumbled across the street and stretched the line. Average response time in the US, 6 minutes. That doesn't include the time to get the call, the time to have it witnessed, the time to process the call, and the time to get you on the road. All these things add up. So ultimately, once you vent it, you had 8 minutes and 30 seconds until it went to flashover. How many people, even if your trucks and engines don't even know each other and don't even train together, could probably figure out opening up the house and getting water on the fire in 8.5 minutes? Probably. To say that firefighting used to be somewhat easier, I don't know that I'll go there, but the timeline is shrinking. Your coordination window is shrinking because of the fuel loads that are in today's structures are changing. And now we're going to bombard you with an engineering graph. This is easy. A couple things I want to point out. Notice that the modern line, modern temperatures, which is the blue line, hits 1100 degrees before it begins to run out of air. So that pendulum's kicking up pretty high, and when it begins to run out of air, it drops all the way down to about 400 degrees because it's starving. It drops 700 degrees because it ran out of oxygen, and that happens pretty quickly. Compare that to your legacy, which is your red line. That fire's only hitting 400 degrees before it begins to run out of oxygen, and then it drops down to the 200 range. Now we're starting to talk about, all right, well, what are people being exposed to? What are the occupants being exposed to before you get there? Well, you're looking at ceiling temperatures of 1100 versus 400 before the fire runs out of air. Chances of having more people unconscious? Absolutely. Chances of having people close to the fire dead? Absolutely. But there are survivable places in that house, especially if you look at the oxygen. The oxygen's on the right-hand side of the graph. Now we're looking at the green line. The modern oxygen drops all the way down to 5% as that fire runs out of air. The legacy only drops to about 17 or 18% before that fire can't continue to grow. Now you'll start seeing that the temperature that a fire gets to and the oxygen concentration really dictate how much it can burn. So it's very different today than it used to be. Excuse me. Now we're going to continue along with the void spaces. More void spaces today than there has been in the past because of open web trusses and things along these lines. And attic spaces. You're going to see when the fire actually does transition from a content fire to a structure fire, it's got more fuel available to it in the void spaces, and it's got more air available to it in the void spaces because of the construction practices we use today. If you had a fire that used to start in the void, it would only have oxygen from one joist bay. Now it's got the entire void space to pull from. But the thing that I'm more concerned with is not the fire that starts in the void space, because that's slow to begin with, but the fire that starts in the contents and spreads into the structure itself is going to be taken off quite a bit, especially if you look at how our attics work. You've got a whole bunch of fuel. You've got it in a peak shape. It pulls air in low and sends hot gases out high. If you were to build a campfire, that's exactly how you would build it, and that's how we build our attic spaces. That's why attic fires can be so challenging, is because you got a whole lot of surface area and a whole lot of ability to burn and for it to get air. Sheathing. Let's look at the evolution here. We've gone from solid boards to plywood to OSB to asphalt fiberboard to cardboard to foam. Excuse me, I'm getting over a cold. very different burning. Here's cedar versus vinyl meant to simulate cedar. The bottom pictures are 2 minutes after the top picture. What you're going to respond to of an exterior fire is going to be very different today than it would be in the past. Wall linings, lath and plaster to drywall. The chance of having a structure fire, when we added gypsum board, we now added seams all over that wall. The chance of that fire going from a compartment fire to a structure fire is going to be much greater today. Structural components. We talked about this a little bit earlier. Dimensional lumber, old growth to new growth, density changes, burning behavior changes, engineered lumber. Then all of a sudden, we're going to make the web smaller. All of this is removing mass. All of it's removing redundancy to buy you more time. It's working against you. Now, in order to make it convenient for construction practices, we're going to cut out the webs and things like that so we can run wires and ducts and everything else. Less wood, less burn time till collapse. That's all it comes down to. It's not the gusset plates. It's not the glue. There's less stuff there to burn to maintain structural integrity. It's going to collapse earlier. And it doesn't matter whether it's old dimensional lumber, new dimensional lumber, or engineered components, collapse should be in your thought process. Insulation. We're moving from a fiberglass insulation to spray foam insulation. New energy requirements, new products in order to meet those new energy requirements. You're going to start seeing foam sprayed on the underside of decks in the attics to go ahead and make that part of the conditioned space of the house. So it's going to behave differently. Here's a test we ran in Delaware County, Pennsylvania. We had one fiberglass roof against one spray foam roof. We were looking at the impact of vertical ventilation. So we pre-cut a 4-foot by 4-foot hole over top of the fire. The fire started in the attic space and it's contained to the attic space. What I want you to watch is the fire behavior that happens here. Because we cut that hole and we put a piece of 5/8 inch OSB over top of it, so it's got like a 50-pound piece of wood covering it up, we ran some instruments to measure the speed of the gases coming out. So there's kind of a low pressure there around the gaps around the piece of wood. And I want you to watch what happens as this fire is involving the spray foam insulation. Pay no attention to that. There's a police gun range there as well. So the fire itself is not shooting gunfire. See the amount of pressure this fire is creating? And you're going to see the fire triangle right in front of you. That piece of wood that's covering up that vent hole is bouncing a foot off the roof. What happened? Fire ran out of air. As it runs out of air, it can't continue to grow and spread. No water's being put on that. So whether or not you showed up 30 seconds before or 30 seconds after, you're going to see very different size up things. And oh, by the way, your structures aren't going to have a 4x4 hole pre-cut for you that you can pull a wire and open it up. So if we didn't have that as a pressure, essentially a pressure relief valve for that fire, where's that fire going? I don't know. We have to do more to figure it out, but it could be through a piece of weak gypsum board. It could be through HVAC vents. It could be any number of ways that that could find a way to force its way into the structure. It could be after you stick a hook in the ceiling that it gets some air and go ahead and responds very quickly. We've got more to learn on this stuff, but I wanted to show you that fire behavior. Last component, new technologies. Who's got solar panels on structures in their response area? You know how to safely operate around solar panels? If you told your chief that, sorry chief, we're going to have to wait till the sun goes down till we fight this fire, probably not an option. There's some safe considerations. We did an entire project, and you can go to our website and see the results of it, where we burned full-size systems. We looked at what happens when you put a saw through 600-volt DC line. If you put a halogen bar into the panel, how much your gear can protect you, what types of salvage tarps actually work and don't work to cut the power off. But the truth of the matter is you've got 600 volts potential being generated on that roof. It doesn't take much sunlight to do that. You don't know where the wires run in that house to get to the inverter that's changing that from DC power to AC power and feeding it into the house. So if you go into the garage or you go into the basement and you throw the disconnects and that inverter discharges and reads 0, that means it's reading 0 going into the house on the AC side. That system is still energized from the first disconnect all the way back to the panels. So if you get a fire that involves that wiring and you put a saw or you put a hook into those wires, it could be a bad day. But there's ways to deal with that. One of the important things I want to tell you is don't be scared to put water on the panels to put the fire out if it involves the panels. But 2 important considerations with that. If you're using a straight stream or a smooth bore, you need to be more than 20 feet away. Or if you do have a combination nozzle, you want to put it on a very slight fog pattern to keep that electricity from being able to travel your stream back to the nozzle. So if that's an option, that's absolutely what you want to do. And a bonus to the fire formula, home lots are getting smaller. So we're building bigger houses, and we're building them on smaller lots. So guess what? All kinds of exposure issues in many cases. Combine that with the fact that we're wrapping our houses in plastic and everything else. And I'd like to say that, well, a lot of these are in sprinkler communities. Well, there's not sprinklers on the outside and there's not sprinklers in the attic. So if you get a fire that starts on the outside because of grilling, starts in the garage for whatever reason, starts in the attic space, it's possible that you're going to see some fires that involve multiple structures upon your arrival because the amount of energy that's being produced on the outside of these houses is tremendous. And it might not look like a lot moving from 10,100 square feet to 8,800 square feet, but the number of giant lots out there on the acres, it's hard to move that number. And we keep moving that number to a pretty small average lot size of 8,800 square feet. So to sum it all up, houses are getting larger, lots are getting smaller, fuel loads have changed, resulting in fuel-rich conditions. Home designs are more open, meaning there's less compartmentation, they're taking advantage of the structural members. They're more energy efficient, multi-pane windows, we're wrapping them in plastic, alternative energy sources we're putting in the basement and strapping to the roof. Evolutions in building materials are changing your fire environment, and they're changing them faster than even us in research that study this full time can keep up with it. As soon as we think we're studying the latest and greatest sheathing material for a house, a new one's in the production lines coming out, and there's nothing that says that energy efficiency is going to trump fire safety most times. So it's hard to catch up. So it's not easy to make the standards keep up, make the codes keep up, make your knowledge keep up with what you're going to be responding to. So ultimately, you have to ask yourself the question, have staffing, training, and tactics changed to adapt to all these changes? And the answer is probably no. And we're going to try and change that because we're going to give you a whole boatload of information that allow you to understand the fire environment that you're operating in a lot better right now. I'm going to pass it to Dan. He's going to get into the fire dynamics, and then we'll get into tactics.
We're going to keep up the pace, but sort of change direction a little bit. We're going to go back to some basics. As Steve said earlier, fire dynamics is taking chemistry, fire behavior, materials analysis, things from mechanical engineering such as heat transfer, fluid mechanics, and putting them all together to understand fire behavior. Now, the first textbook in fire dynamics wasn't written until 1986. So this is a relatively new science. This is a relatively new area of study. That textbook, needless to say, wasn't written for firefighters, right? It was written for other engineers, other scientists, other researchers. So now we finally advanced to the point that there's been an area referred to as the golden age of fire science, if you will, that sort of ran from the late 60s, starting with the Home Fires Project at Harvard University, got into the creation of the Center for Fire Research at NBS, which is now NIST, where I work. And some people say it sort of ended around the late 80s, early 90s. And it basically took that amount of time for them to really understand a lot of physics regarding the fire in a single room. And now we're getting a better understanding as the technology advances with both fire modeling and fire experimentation, understanding fires in full structures, and actually going out and running tests with the fire service to understand the fire dynamics of fires in full structures. So what is a fire? Well, for one thing, you can't burn a solid and you can't burn a liquid, right? So the reason is because the fire is a gas phase chemical reaction. And we say it's exothermic, which means it gives off heat, it gives off energy. And we say that it's an oxidation process, which means that it requires oxygen to generate that energy. If there's no oxygen, there's no chemical reaction, there's no energy given off. Everybody knows about the fire triangle, the fire tetrahedron. We need fuel, we need oxidizing agent, we need heat, and then we need this chemical reaction, this self-sustaining chemical chain reaction that needs to keep going to generate sustaining flames. Everybody was in the class this morning. We talked a little bit about your traditional fire behavior where the graph on the left ought to be pretty familiar, where you have ignition, growth, fully developed. You might have flashover or a backdraft right at that bend for the fully developed stage, and then decay. And that's typically driven by fuel. Then we have the ventilation controlled fire. And that's more typical of the fires that you're going to encounter on the street today, unless the homeowner leaves doors open or something when they leave that fire area. But again, with the changes in insulation, the desire to keep as much of when we're normally heating or cooling our homes, we want to conserve energy, right? We want to keep the heat in or the cool in, whatever we're producing at that season of the year. Well, the result of that is there's not very much air exchange with the outside. So it means there's not going to be a lot of leakage once a fire starts in that house. It's going to hold all that gaseous fuel inside. So smoke is fuel. I have to click this one. Easy demonstration, you can do it at the kitchen table. Take a candle, blow it out, bring the match to the gases that are coming off the candle wick, and you'll see the flame goes back to the wick, right? Smoke is fuel. What's in that smoke? Well, we have basically that glow are carbon particles under a high state of energy that are beating and banging against each other and glowing. And if we cool them off by having them condense out on a piece of metal like a spoon, what's going to happen to the spoon? It's going to get sooty, right? So that's the fuel that's contained in there, giving you a representation of some of the fuel that's trapped in there that'll burn. So solids don't burn, liquids don't burn. If we want to have carpeting or a sofa or a wood piece of wood burn, we need to pyrolyze it. Fancy word. Just means we're applying heat to this thing, and due to that heat alone, it's breaking down the materials into a gaseous fuel. If you only take one video home to show them, well, I guess two. The Steve's comparison video is a pretty telling video, and this one for fire dynamics sort of shows everything you need to demonstrate. We've got a dry Christmas tree in a 12 by 12 living room with some furniture in there and an open doorway. Notice how the excess fuel is spreading across the wall and how the flames start to follow that fuel down, right? That's the fire triangle in action. Hot gas, oxygen, and fuel. Next, we're going to see the radiant heat transfer from the flames start to pyrolyze the sofa and the chair. So we have blue polyester covering on the chair, and you see it turn into a white vapor. That's raw fuel. That fuel's going up into the upper layer, the hot gas layer. The hot gas layer starts to burn. We have rollover. The radiation from that starts to pyrolyze the carpet and every other fuel that we have in there. It's going to entrain a lot of oxygen through the doorway. There's going to be very turbulent mixing, and we're going to transition to flashover, and then that room's going to do what? It's going to start to darken down because it doesn't have enough oxygen inside to breathe. Where's the fire? It moved outside that open doorway to be a 8 to 10 foot tall flame outside that doorway because it can't breathe in there. Heat transfer. So what were the conditions inside? What if you were inside that room? Could you survive? Probably not. Sometimes you'll hear people talk about this condition referred to as black fire. That's when the gases are hot enough to be flames, but they don't have the oxygen to burn, and they're getting pushed or moving through a structure. So heat transfer. Without heat transfer, you can't ignite anything, you can't have fire growth. At the same point in time, if you put water on something, if you don't have heat transfer, you can't have the fire go out either. So heat transfer is very important. Again, basic physics. There's some laws of physics here. Heat transfer only goes in one direction, from hot to cold. Right? Mechanisms of heat transfer. Again, firefighter 1 type of stuff. Conduction, convection, radiation. Conduction is heat transfer within solids. Convection is heat transfer between gases or between liquids and gases or gases and solids. So for example, when the fire plume goes and hits the ceiling and turns into a ceiling jet, those gases are rolling the ceiling. It's transferring heat to the ceiling via convection. Radiation is heat transfer by light energy, so you have to have line of sight. So if you're not directly between the emitter, whether it's the flame or the hot gases overhead, you can shield yourself from the radiation. Basically, if you're standing out in the sun and you step into the shade, right, you got out of the direct radiant light from the sun. Same kind of thing. Showing you a few, not all equations, but a few so you understand the process. So this is convection. So that Q dot in scientist lingo is heat rate, heat transfer. And it equals a convection heat transfer coefficient, H, times the difference of T hot versus T cold. So in this particular case, T hot are the gases coming off that fire, and T cold is the initial wall temperature. And then the last thing we multiply by is the area of the target, or the area of the wall. Now that wall could be you in your turnout gear, right? You could be the target for that heat. So one thing you notice right away is that TQ, or Q dot, is going to be bigger if the difference between T hot and T cold is bigger, right? So if that difference, instead of being, let's say you were 70 degrees when you went in there and the fire environment's 150 degrees, well, that piece in between would be 80. Well, if it's 400 degrees in there and you were 100 degrees by the time you got there, now that interior piece, our delta T, is going to be 300 degrees. So you can see a direct relation there that if you go into a hotter room, the heat transfer between you and the hot gases in that room is going to be larger. Now here's the part that might not be so intuitive, and that's that H factor. And the H factor is basically how turbulent that gas flow is across your body, how fast it is. And so if you have a laminar flow, not very well mixed, very slow, we might multiply that delta T by 5. But if you have a high flow rate, high velocity, well-mixed, churning gases that are going over you, now we might multiply that delta T by 50 or by 100. This is basically the equation. You may be more familiar with wind chill, right? When you go outside in the wintertime, they tell you, well, the gas temperature, the air temperature is 40 today, but we got a 20-mile-an-hour wind. So when you go outside today, it's going to feel like 28. That's this equation, basically. So why does it feel like that? Because the rate of heat transfer to your skin is faster than your skin can keep up with heating your skin. Whoa. So molecules of air, cold molecules are coming across your hot skin, right? Hot goes to cold. It picks up the heat and moves on. As we increase the wind, just as we increase the air velocity, more cold molecules are hitting your skin and taking away more heat. And as a result, your skin cools down because your body's not creating enough heat to keep up, so you feel colder. Well, now when you're in a fire environment and hot goes to cold, you're probably the coldest thing in that fire environment. And now if we put hot gases with a high velocity over you, now it's more like having the hairdryer at home, right? You turn it up on high, you move your finger in front of the nozzle, and it feels a lot hotter than when it was on low. right? You're increasing the heat transfer rate. So the air temperature didn't change, but the amount of air going over your body changed, and as a result, you're getting hotter and your gear can't protect you for as long a time. So again, when we have forced convection, it could be anywhere from multiplying that delta T by 10, and 500 is sort of the rear end of a jet engine. So I mean, that's another extreme. But the key thing is, if that Q dot gets bigger, it's not good for you. How else might we use this? So I mean, this is a good thing to kind of keep in mind. Let's say that you show up at a fire training event, and some person, could be an experienced person, could be a scientist you never heard of before, says, you know what, I think the best idea is when you've got flames rolling the ceiling, let's put the water on the floor. I'm going to show you. We're going to go in this 20 by 20, this 20-foot sea tainer, and look, the flames are rolling the ceiling, and I'm going to get down here, and I open up the hose line, and the water goes on the floor, and the fire went out. And you might walk away saying, damn, fire went out. That's pretty neat. Well, that was in a sea tainer, right? Let's look at the physics. If you want to increase your Q dot, if you want to increase your heat transfer, where do you want to put your cold water? You want to put your cold water in the hottest places possible. So if you've got 1,800-degree flames up here and 400 degrees down at the floor, where do you want to put your water to make the most sense? Right? Get it in the hot stuff. Now, that said, if you've got a small room, maybe it doesn't so much matter where you're going to put the water. Just get the water in there, right? But just something to think about as you hear different things over time. Convective heat transfer, back to the candle. If we take a candle and we make a measurement over the candle, you see our sensor there is within about 1 inch of the candle flame. As we move the sensor over the center line of the candle, we're seeing 80 to 100 kilowatts per meter squared of energy, which is why you can light many things on fire with just a small open flame. Very close to it, right in its center line, has a tremendous amount of energy. So let's sort of look at our threats, our hazards. We have a early growth stage fire shown there. There's a open door where fresh air is coming in behind the firefighter, and radiant energy, a little bit's coming from the chair and some is coming down from the hot gas layer. That's transferring energy to the firefighter. Convection, again, early stage. This is sort of the ideal situation here, where the convected air that's coming in the door, low, is actually cooler than the fire environment inside, and that's helping take some of that heat that was transferred by radiation away from you. So that's a good thing. But notice where the high heat, high pressure gases are exiting out the top. So one might imagine that if you were to be in where the red arrow is, that could be bad, right? The heat transfer to you is going to be increasing. So if the hot gas layer comes down to where you are and is flowing over you, you're in trouble. Conduction. A lot of times we just think about conduction being, you know, where you're touching something, where you might be your gloves on the floor or on a hot surface, or your knees crawling on a hot floor. But the other thing to remember is, how does your gear protect you? Your gear protects you by absorbing energy and storing it. And then what happens? The gear gets pretty hot. What direction does heat flow? Hot to cold. What's the next cold thing? You inside the gear. So at some point in time, that's the gear that's touching and pressing against your skin is going to be conducting through that gear into your body. So when your gear's hot, the last thing you want to do is have it compressed against your skin. If one of your fellow firefighters gets his trim on fire and you have this, you know, temptation to pat it out to put the fire out, you're really not helping him, right? You're going to push the hot gear against the skin, make the burn injury worse. Cool them off. Throw water on them, get the gear off. You got to get the heat moving away. You want to change the direction of the heat from going to him to somewhere cooler to going away from him. Firefighting thermal environments. So in the green box there, on the bottom we have heat flux, kilowatts per meter squared, and that's again this radiant energy. And vertically we have air temperature, which will control our convection heat transfer. So we've got convection on one side, radiant heat transfer on the other side. And the key thing to remember is that these two sources of energy from the fire add up, right? If they're absorbed in your gear, they add up. So routine case, 1 to 2 kilowatts per meter squared, and up to about 160 degrees Fahrenheit is sort of the routine case. That means your gear can protect you probably for on the order of 10 to 15 minutes under those type of steady state conditions. We get into the ordinary case, and that starts at our sort of 2 kilowatts per meter squared and 140 degrees Fahrenheit, and goes up to a peak of 400 degrees Fahrenheit and about 12 kilowatts per meter squared. Once we get to that upper corner of ordinary, now you're sort of in that kind of 2-minute range of protection. And once you get, again, but part of this depends on how hot were you before you got in that condition, right? And then we have the emergency condition where we're kind of considering that less than a minute, right? You need to be making your way out of that space or changing the condition of that space pretty dramatically under those sorts of situations. So I'm going to show you a couple of films here. We have a chair that weighs 42 pounds. I've got 2 of them in there, polyurethane foam and polyester batting. And here I've got 1 window and 1 door to this compartment that's about 12 feet by 10 feet by 8 feet tall, and the door and the window are both closed. And you're going to watch the fire develop, you're going to watch the smoke grow, and just under the window you saw a couple of squares on the wall. That's firefighter turnout gear that we have instrumentation in. So the smoke layer comes down over the firefighter turnout gear. What's happening to the fire right now? Starting to run out of oxygen. The hot gas layer is coming down below the level where the fire can entrain fresh air. So if we don't do something quick, that fire is going to go out. It got hot, it started to build a little pressure, smoke started to force its way around the cracks in the doors. You see it pushing out there a little bit. So we're going to open the door. The fire was still in the early growth stage, right? So as a result, what happens? Opening that door works. Hot gases are going out the top. High pressure hot gases going out the top of the door, and fresh air that's at lower pressure gets entrained, basically pulled in by the fire into the lower level. What do you see happen? The smoke layer lifted. You could see, you know exactly where the fire is. I've slowed the video down to real time, and watch the lower right-hand corner, and we're going to start to see rollover. And when you see rollover, you're going to notice the flames are going to go across, break the interior pane of the double pane window, but not fail the window totally. Notice that the flames are going to burn at the interface of the hot gas layer and move toward the door. They're going to move toward the source of oxygen. And you see how the radiant energy increases, pyrolyzing the carpet as it does that. And now we're going to sort of stop it just short of flashover by hitting it with a sprinkler. So here we have a graph. I'm going to show you a number of graphs. So basically we've got the temperatures starting from 1 inch below the ceiling, the blue line. Then we come down a foot, and then they're every foot until we get to 1 foot above the floor, which is that sort of neon green line. So you can see that we got to temperatures on the order of 300 degrees Fahrenheit, 1 foot above the floor, within about 3 minutes of ignition. So what's that tell you about occupant viability if somebody happened to be stuck in that room? Not very good. Notice how the temperatures drop off a little bit until we open the door. Now notice what happens to the graph once we open the door. The conditions separate, right? And you saw it in the video. We once again have a hot gas layer and a cool lower layer. So the temperatures 3 feet above the floor and down, where you would be crawling, are ambient conditions. They're 100 degrees, just as it was that day when we were running the test. That's the outside air conditions that you'd be exposed to. And life is good, perfect working environment, fully encapsulated in your gear. You're well protected to work under those conditions. You have about a little bit of heat flux hitting you, less than 5 kilowatts or so. Life is good until what happens? Until rollover. Once that rollover occurs and we've got flames rolling the ceiling, the radiation kicks up, the convection keeps up because the hot gas layer comes down, and you see how rapidly conditions change. We go from you being in a safe environment to you being in an untenable environment in about 20 to 30 seconds. So there's a measure of total heat flux, which is convection and radiation added up. That's the blue line, and the green line is the radiation alone. So we get up to 50 kilowatts per meter squared very quickly. Now your gear is tested to what level? Anybody know in the TPP test? 84 kilowatts per meter squared. Any idea how long you would be safe or how long you should have before a second degree burn injury with a TPP rating of 35, in theory? 8 seconds. In theory, it's 17 seconds, but you know, if you assume it's compressed a little bit or dirty, or you know, you got a little preheated before you got there, the key thing is you don't have a lot of time, right? You've got to be moving. If flame's impinging on you, you've got to be moving, and you can see how quickly those things change. Here's the temperature of the PPE that was on the wall. So the outer layer temperature was sitting at about 200 degrees, and the inner layer temperature, the green line, is a little bit less. So assuming you have a station work uniform and you're centered in your gear, right? Keep the hot gear off you a little bit, you're going to be working in there. You can be okay. When you see them both make that vertical turn, that's sort of your safe time, a little less than 20 seconds, between when the blue line turns north and the green line turns north, and then you're burned. Heat flux inside the gear, same kind of story. So now we're going to look at, again, similar room, same kind of fuel load. We've got a 40-pound chair that we're going to ignite to start with. Again, you're going to see the thermal plume go up. We're going to see the sealing jet go across the ceiling. When it reaches the walls, it starts to form the hot gas layer. That hot gas layer, which is now a reservoir of fuel, continues to be heated, and more fuel is added to it as the chair burns very inefficiently. We've started out with an open door, so do you think it's going to go to flashover faster or slower? Slower because it's letting heat out, you think, right? Actually, it's going to be faster, right? Because it's got that continual supply of oxygen, right, to feed the fire. So we're going to slow it down to real time again so you can watch the rollover. And notice when the convective layer goes over the turnout gear. Right now it's just hanging a little above the turnout gear. We have our rollover. So at about 180 seconds, 200 seconds is when that turnout gear starts getting bathed in hot gas. Notice how the flames are going toward the door. Now this one we're going to allow to transition to flashover. Look at what the smoke looks like from the outside. Notice where the neutral plane is. The difference between the high pressure hot gas layer and the cold fresh air going in the door is lower than the base of the window. So the window is unidirectional, high pressure pushing out top to bottom, and the door is our only air inlet. What you see there, that pulsation of fire, you might consider that pushing fire. That's ventilation due to how it's getting the oxygen in to mix with it, and when it can burn and when it can't burn. Basically, we need the fuel to lean out a little bit before we get flames continuously out of that window and out of that door. Is that a hard fire to fight? Not from the outside. Right? So fires like that, in previous cases, we've introduced, let's say, 2 gallons of water by throwing a bucket in the window or in the door. It darkens the fire out for a short period of time. If you don't have another bucket of water pretty quick, it's going to come back like a banshee in no time. But again, the fire can't breathe. That's why the flames are moving out of the door. It's very fuel rich, and introducing some water into the compartment while the fire is still trapped in the box, so to speak, is very, very effective. So there we see our thermal gradient, our temperatures again from the floor, from the ceiling down to the floor. Initially, we have temperatures at the ceiling sitting around 390 or 400 degrees. Near the floor, they're ambient conditions until we have rollover. You see they rapidly increase until we reach post-flashover, which would be defined as temperatures in excess of 600 degrees C or 1100 F. That also happens to be the auto-ignition temperature of carbon monoxide. So we're sitting at temperatures floor to ceiling in that space around 1500 degrees Fahrenheit. Notice introducing the hose stream from outside drops the temperatures very quickly to about 200 F. Heat flux, again, now we're up to about 75 total heat flux. The radiant heat flux is up to about 30 because we allowed it to transition to flashover. The PPE temperatures, again, you're okay. The outer temperatures are below 200 degrees Fahrenheit. Inside the gear is less until we have rollover. So when did the hot gas layer come down over the turnout gear? At around 180 to 200 seconds. Well, there you can see it in the graph. Right, so as soon as those hot gases start impinging on your gear, your time of safety, of safe operating is gone. You need to be moving or changing the environment. Flow path. So basically, flow path is the volume in a building a series of rooms or hallways or corridors or stairwells that's between an inlet and an outlet. So I got some gray hair in here, so some of you guys might have been hot rodding back in the day, right? So if you consider the fire structure as your internal combustion engine, and your inlet was your carburetor, and your outlet was your exhaust system, if you wanted to get more energy, more horsepower out of that car, what did you do? First time you got your check from working at Safeway or whatever, what did you do? You had to go get some hooker headers, man, and some glass packs. Got to let it breathe, right? Got to open up that exhaust. Got to get that Holley 750, you know. You got to get that big carb on there to increase the flow path. Make the engine a better air pump and fuel pump and let it burn better. Well, that's really what we're talking about here with the structure. Whether you want to use the analogy of an automobile or the analogy of a wood stove with the damper controlling the exit of the flow path and either the front door where you're loading the fuel in, it's the same kind of deal, except now we're talking about structures. And when we're talking about basement fires, if you want to use that analogy of the wood stove, now you got a wood stove that's made of wood, you're dancing on top of it, and you're going to open the damper and open the inlet and think things are going to turn out well. So that's really what we're talking about here. So here's a wind-driven case, the first one that I was involved with, where flow path became a big issue. Vandalia Avenue in New York City. You look at the apartment building on the downwind side and on the upwind side, and you see that there's soot stains that are pretty similar. And so one of the questions was, geez, you know, which of these from outside, which one is the fire apartment? Well, the fire apartment was on the upwind side. And a little old lady lived there. She just got new carpeting. She was going to have a party, a little get-together, wine and cheese party with some of her neighbors. This was a senior living facility. And so she had the fact that the new carpet kept her front door open wasn't a big issue for her. It was actually going to work out for her that night. You know, the self-door closers weren't going to get the door closed tonight because the new high pile on her new carpet. And so the door was open. And around 11:30 or so in the evening, one of her neighbors noticed that she was relaxing on a sofa in front of these windows having a cigarette. About 4:30 in the morning, the fire alarms in the building go off. And the fire department arrives, and Lieutenant Cavalieri, Firefighter Bohan, and Firefighter Bopp come in from the elevator lobby and start making their way down the hallway. They were accompanied by a captain from an engine company. He left them at that point. They looked down the hall, a little bit of smoke, not too bad. You know, let's go see what we need to do. There's a lady in the apartment next to the fire apartment, and she calls 911. She's in a wheelchair, and she needs to be rescued. And so a crew comes up the stairs here, and they bring her out, and she's treated for smoke inhalation and released that day. There's a little old guy in this apartment down here. Now, he's getting some smoke in his apartment. He doesn't like that. So apparently when he's had smoke in his apartment before from cooking or whatnot, what he did to get rid of it was open the windows. Well, now, this is the upwind side, high pressure, and this is the downwind side, low pressure. Right? So just like hot goes to cold, high pressure always goes to low pressure. So when he opens that window, he creates a flow path. Right? And so that flow path is now coming from the fire apartment down the hall and out his apartment. So he's getting more smoke in his apartment. So he decides he's going to leave. So he opens his apartment door. He gets even more smoke. He doesn't like that. He leaves his apartment door open, and he goes into his bedroom, and he safely rides out the fire. So now Firefighter Bohan, Firefighter Bopp, and Lieutenant Cavalieri are between where the fire is and where the fire wants to go. They're in this area here. When the window fails on this fire apartment, that heat release rate of the fire increases due to the increased level of oxygen. The fire comes out in the hall, and due to the pressure from the wind, the fire gets driven out into the hall, and as a result, Lieutenant Cavalieri, Firefighter Bohan, Firefighter Bopp die. Firefighter Bopp got a mayday off very quickly. Firefighters here now open this door again, and as was the practice in New York City at the time, they would send their roof man up, and he would open the bulkhead door and keep it open for the duration of the fire. The roof man in this case was going back and forth telling them, high wind condition, I see flame pushing in and out of the window of the fire apartment. But that because the bulkhead door is open, and when this door gets open now, that's part of the flow path as well. So the first hose crew gets burned, they can't advance the line. Eventually, they advance a 1.75" line and a 2.5" line down the hall, and unfortunately not in time to save the other members. So this is what the hallway looked like between the fire apartment doorway and the attack stair doorway. This is looking from the front door of the apartment into the apartment. So you see that the apartment, although it wasn't heavily furnished, it had a sofa or two in it, and basically a wood dining room set, again lightly upholstered. It had burned long enough it got back into the wall and picked up some foam insulation that was burning on the outside wall as well. It burned hot enough that it spalled the ceiling planks that formed the ceiling of this apartment. So a lot of energy was released. So before our fire dynamics simulator even had its name, we ran a model with it. The blue box represents the wind, and the fire apartment is right in front of the blue box there. And this is the little old man's apartment, and then of course we have the stairwell on the opposite side. So what you'll see is when the window breaks, the fire size is going to increase and smoke is going to start to move down the hall. And because the roof man said that the flames were pulsing in and out of the window, I assumed that the wind was fluctuating. So when I modeled it, I had the wind go up to 20 miles an hour and then back down to 0. So every time you see a wind pulse in the model, flames and heat will move down the hall. In response to the Mayday, now the door to the stairwell is going to open, and then you'll see smoke and flames move into the stairwell as well, to basically heading toward the bulkhead doorway. So plenty of fuel there. The flame, it could split. Even though it appeared vented from the street, there was still plenty of fire and energy that put these firefighters in jeopardy. So 10 years later, we get an opportunity to run a project to really study this wind-driven fire phenomena. And as I described a little bit earlier in the class, we have this flow path where basically we have the bedroom, we have a hallway, we've got a target room here, there's a hollow core door between the target room and this hallway, and then the living room and our outlets, non-flow side and flow side. So I'm going to go through this again quickly, reminding you that you only need one piece of furniture to flash over, to have enough energy to flash over a typical residential scale room. And we'll watch this video again. So again, our fire starts here in the bedroom. We have our plume starting to impinge on the ceiling. Ceiling jet moves across the ceiling. Once it hits the walls and forms the hot gas layer, it starts to build up in depth and then spread down the hallway and into the living room. And notice that when it starts to flow out the doorway into this corridor, it's going to head for this vent, right? The flow is very directional away from the camera toward the vent, part of the flow path. Right now, if you were to get there right now and start to make an attack and work your way down the hall to get to the fire bedroom, this is sort of that old school early growth stage. You're there in time. It hasn't gone into a decay stage yet. But now that's transitioning to a decay stage. And as soon as this window, which might fail accidentally or might be ventilated as a ventilation tactic, look at what it does in that hallway. Right? It's no longer a hot gas layer, cold layer environment. Now any firefighter that would be in that hallway is in that hot convective flow. Heat transfer to that firefighter increases dramatically. We're going to watch the hollow core door fail. Interestingly enough, until that door fails, somebody would have a chance of surviving behind that door. Right? So I mean, from a victim's perspective, having a closed door doing whatever compartmentation you can is a big value. Notice how that flame is pulsing in and out. Now this is with no wind. So again, very dramatic increase in heat release rate. It goes from about 2 megawatts to 13 to 14 megawatts within 60 seconds. The bedroom temperatures. Initially, we had over 1,000 degrees at the ceiling and about 500 degrees at the floor. Once the windows vented, now floor to ceiling, we're post flashover. We have a very well mixed fire going from floor to ceiling in excess of 1,100 degrees Fahrenheit, and it stays that way until suppression. The living room temperatures So what's happening in the living room is there's not really a lot of fire in the living room. Why not? There's temperatures at the ceiling that are about 700 degrees. They're pretty warm. So what's going on is the temperatures and the heat flux in the living room are hot enough to start to pyrolyze the furniture and the carpeting that are in the living room. So gaseous fuel is being created, but it doesn't have any oxygen down there to burn. Then when we vent the window, it starts to pick up some oxygen, but it's still burning pretty inefficiently because you see, we're not post-flashover yet. We still have a temperature gradient, although now the ceiling temperatures are about 1,400 degrees Fahrenheit, and near 1 foot above the floor, it's about 800 degrees Fahrenheit. When that door fails to the target room, the chunk of oxygen that's stuck in that target room gets pulled out into the hall, and that's what causes this increase in temperature here, and then we sort of transition to our flashover state. The velocity in the hallway. High pressure wants to go to low pressure. So initially, with that window in place, we don't have this big exchange between high pressure and low pressure, and we just have the ceiling jet that's going across the ceiling at about 9 miles an hour or so. Once the window's gone, we have this well-mixed fire environment, high pressure in the bedroom, forcing its way to the low pressure in the living room, so the conditions in the hallway, floor to ceiling, are now somewhere between, say, 8 miles an hour and 12 miles an hour. Right? So this is that H factor in that convection heat transfer equation that's increasing the heat transfer to any target that's in that hallway. Living room, gas concentrations at 6 feet. This is oxygen. The red line is oxygen. The yellow line is carbon dioxide. The sort of triangles here, this green line is carbon monoxide, or CO, and then this purple line are the total on-burn hydrocarbons. This is the excess fuel that's still in the living room to burn. So you can see the oxygen concentration went way down, CO2 way up, CO way up. So the CO is sitting at about 6%. That's 60,000 parts per million. So when you get to about 3% CO, that's one breath that will drop a person in their tracks, an unprotected person. What about at 2 feet above the floor in the living room? Well, we still don't have a lot of oxygen down there. Our CO2 is above 15%, and our CO is in excess, again, of sitting around 6%. So a very unhealthy environment for all involved. Total on-burn hydrocarbons in the living room, we've got about 12%. So again, there's more. If it just had more oxygen, it could burn those on-burn hydrocarbons, right? The heat is there, the fuel is there, it just needs more oxygen to burn. So if you vertically vented that room, what would happen? It would burn hotter. The heat release rate would increase. If you broke an additional window on that room, the heat release rate would increase because it's got excess fuel to burn and it's already preheated, ready to go. Now we're going to add some wind. So in this case, I'm letting you look at the inlet, which is the window, and the outlet, which is the door from the fire apartment to the corridor. I've got a 20-mile-an-hour wind, steady wind, hitting the side of that building. Notice that in the corridor we have a nice 2-layer environment, which are good working conditions for a firefighter. Look what happened when the window broke. Look at how rapidly that changed. This is playing in real time. What do you notice about the flames at the window, even though I have a steady 20-mile-an-hour wind? They're pulsing in and out, just like the roof man from Vandalia said. The key thing is we didn't understand it at that point in time. The pressure is so high in that apartment, it can't force it all out through the exit, so in effect, it's burping itself to relieve the pressure and then sucking back in the window. Here's another case. In this case, the apartment door is closed. Right? So you'll notice that with the apartment door closed, this is having a hard time even failing the window, right? Because the pressure is bottled up in that fire apartment. So now we break the window. It's still burning very inefficiently. It's having trouble breathing. And the apartment door, is providing protection. It's cutting off the flow path. You can see the leakage, and there's a lot of energy on the other side of that door. You can see that with the thermal imager. Now the key thing here is, this might be the sort of situation where you get your crew, you'd have your line charged, and you say, okay, we're going to get low, we're going to pop the door, and we're going to go in. And that would really be a disaster because you see the kind of thermal assault you're going to take right in front of that door. and flowing a line, unless you can get the fire gases where they're originating back here, you're not going to have a lot of impact on that. You'd be much better off introducing water from this side, either with a high-rise nozzle or a wind control device to cover it, to cut the flow path, things that New York is working on. Impact of the door. Again, this line is where we open the door times 0, and the red line is 3 feet above the floor in the bedroom. The yellow line is 3 feet above the floor in the living room, and the other lines are out in the corridor. The purple one being in the flow path and the other two being on the non-flow path side. So what you notice very rapidly, as we talked about before, the fuel is hot enough to be pyrolyzing in the living room. Once that window's open, the temperature in the bedroom cools off initially and then increases to over 1,600 degrees Fahrenheit in a space of less than 10 seconds. The living room also follows suit, and then the flow path in the hallways above 1,000 degrees. All this is occurring within 20 seconds of opening that door. So again, what the wind is basically doing in this case, it's still doing what would happen normally, except it's accelerating the whole process. It's crunching down that timeline. As Steve had said earlier, with such a fuel-rich environment, it's less forgiving than the older fuels that gave you a little more time, gave you a little more options with regard to ventilation and things of that nature. I'm going to show you one last experiment here from this series of tests. And what we're going to do, same as before, we're going to let the fire develop, except this time we're going to put our laboratory at risk for the interest of science. What we're going to do is we're going to let the fire come out of the vertical vent, and basically the smoke is going to build up in our 30-foot by 40-foot hood and auto-ignite and burn. And then we're going to introduce a hose stream into this window. Here's the video view here in the upper left-hand corner, and the lower right-hand corner is the IR view. We're going to introduce a hose stream in there once we have the hood on fire, and look at the impact. So the hose stream's flowing about 80 gallons a minute, and we have about 40 feet of apartment between where they're introducing the hose stream and the fire in the stack. So we're going to watch it develop. Everything's darkened down inside the apartment itself. We see some flames coming up into the stack, and now we're going to ignite the gases that are residing in that stack before they can get sucked up our 6-foot diameter hood. The fireman's getting ready to introduce some water at the window. There it goes. What happened to the fire in the hood? Gone, right within seconds. Now you look at the video view of the room and you say, wait a minute, there's still a lot of fire in that room. Well, there is, but really you'll see as the bedroom view starts to improve for us is that what we have now are a lot of incipient fires. We've got the remains of a couple of chairs in front of the window that are burning. We've got the remains of the bed that are burning. A dresser is burning. But what you've taken out of the equation is this reservoir of hot gases that was burning from one end of the apartment all the way out into our hood. Right? That's been neutralized. That's been taken away just by this hose stream. And you see the view is cleared up in the bedroom view. And then he stands up and knocks the rest of the fire down. So again, taking those fire gases out of play and bringing it back to the fact that you might have just a sofa burning or a chair burning or something like that, that's something you can go inside and deal with. So then we moved into a high-rise, and we went to Governor's Island in New York, and we went there in February because it's cold and windy. So the weatherman says, and history says, about 90% of the time. The whole time we're pulling wires, putting up our instrumentation, loading furniture into the building, very windy, very cold. Then we got a snowstorm, still remained cold, but the wind stopped. So we brought our own wind, and we had the good fortune to have some squad guys take this fan off the back of the manufacturer's pickup truck and lash it to this boom lift, and we put it up 60, 70 feet in the air. So we had our good wind. Again, we're using real fuels. And then we start demonstrating things. So again, now we're working with the fire service. How would you attack this fire? Well, we're going to go in, we're going to open the lobby doors, chock them open. We're going to get to the stairwell, attack stair, we're going to chock it open. We're going to go upstairs, we're going to open the bulkhead, or we're going to get our attack crew set for the stair. And then we start changing it to see how we could make it better. In this case, this graph is just showing you temperatures in the corridor between the fire apartment, which has an open door and wind blowing in the fire apartment, and the bulk and the stairwell door. So this is stairwell 7, the door's closed. The bedroom window is failing, so now we're going to have the wind having an impact. They open the stairwell door a little bit, and you see the temperature in the hallway increase as they start to complete that flow path. Then they open the stairwell the rest of the way, and we open the bulkhead, and that provides our exit. We open the damper on the end of the exhaust in the wood stove, and you see how rapidly the temperatures in the hallway outside the apartment increase from something that might be tenable for a firefighter to work in for a short time to something that's completely untenable for a firefighter in full protective clothing. And you see the time it happens. Each one of these marks down here is 10 seconds. So it's happening in the space of less than 20 seconds. Very rapid transition. This isn't just a high-rise issue. Single-family homes. Here's an incident that happened in Houston. Killed a captain, very experienced captain, more than 25 years on the job, as well as a young firefighter who was 30 days on the job, and this was their first fire. The wind was coming from the rear of the structure, and there was so much smoke in the street in front of the house, and when the fire department arrived, fire sort of happened in the middle of the night, the engineer stopped because he didn't want to hit any parked cars. He wanted to get a better view of where he was going. And then he took the apparatus down the street past the house. They hooked up to a hydrant, and the lines start going in the front door on the low wind side. Now, this was a very difficult house to gain access to the rear. Again, some confusion about whether people were in the house or not. In fact, the occupants were out of the house, and they had opened the garage door to the house to get their cars out. So again, another opening on the downwind side. So here's the front door. The nozzle from the victims was found here. Their line went down the hallway. Their nozzle was found here. And the 2 firefighters' bodies were found in this location here, so they were well off their line. Another engine company was in here. They were flowing water in this area here. They were hooking the ceiling, and as they were getting basically chased out of the fire by high heat conditions, they noticed that they could see these guys' boots back here, that they were still standing at that point in time. The big change in this case was, again, failure of glass. There was a glass patio back here, and when it failed, that changed the flow path, right? That was our inlet, and the exhaust became through the downwind side. The fire had started in the attic. This was an older house, had been added on too many times. In some cases, it actually had a double roof, so there were asphalt shingles actually in the attic providing additional fuel. And you can see how it burned away there. A ladder company was on the roof, and they made some cuts right in this area here. The ladder captain says as soon as they made their first cut, fire came out of it. They kept cutting and did a good job and opened up the space. And he said he looked to the rear of the house, and he noticed that there was a flame overlapping the eaves that was about 1 or 2 feet wide. As soon as they were done with their cut and punching down the ceiling, he looked back again, and now he saw that that flame overlapping the eaves was about 20 feet wide. Well, that's because all that glass, solarium glass, had failed. So again, we're modeling this fire to try to get some understanding of what the flow path looked like and what happened. In our models, we include the roof vents. We try to get the whole timeline down for when they're pulling the ceiling and that sort of thing. And this is what it looks like. So the graphic on the side, anything that's red or above is 500 degrees Fahrenheit or above. So not healthy for a firefighter. Our slice line here is about 3 feet above the floor. Here's our garage door that's open. The door between the kitchen and the garage was also left open by the occupants. And then this is the door the firefighters are going to open to make entry. The wind is coming from this direction. So the front door is open. They open the door, and then what do? Well, you got to get your mask on, get your helmet on, whatnot. Again, this is an issue. When are you making the vent? Right? You don't want to vent till you're ready to take some action. Or if you're going to open the door and take a look and you see conditions aren't so good, close the door again. Right? Don't allow the fire time to build up by entraining more air. So things are heating up. In fact, opening the door, you're going to see when they make the roof cuts right in the foyer area, it'll cool off a little bit. They'll get a little bit of lift. So now the roof is vented. It cools off a little bit in this area. Things are working. And then the glass fails. And now you see where the heat's going. So they couldn't stay on their line and follow their line out probably if they wanted to. They went to an area that was not as hot. It just wasn't cool enough for them to survive. So this is a side view looking at the front entry. So the view on the left is before the wind is impacting it. So you see it's cooler, close to the floor. You could crawl in and under there. Once the wind is blowing through the house, it's dropping the heat, it's mixing it toward the floor. You can't get low enough to get out of the thermal flow. And perhaps more importantly is the velocity of that hot gas. Before the window breaks, 3 feet above the floor or so, fresh air is being entrained inside that front door, bringing cool air into the house, also feeding the fire. But if you're in the location of the doorway as a firefighter, it's going to help you. It's going to help keep you cool. Once the glass breaks, notice what happens. The flow reverses and hot gases are coming out at that same location. Again, no escape. So wind. Keep the wind at your back, stay upwind. Otherwise, you're literally putting your crew at the mercy of whether this glass that's less than a 1/4 inch thick or not is going to break while they're in there, or whether somebody from another company in an uncoordinated manner makes a vent and puts them in harm's way, puts them in the flow path. Again, just a top-down view. This is the direction of the wind out to the front door and out through the garage. So they couldn't go this way, they couldn't go this way. There were security bars on the windows here. They got to the best place they could and couldn't get any further. Again, you'll see where the flow path is because that's where most of the burn damage will be, because that's where the oxygen's mixing with the fire. So it brings us to some questions about ventilation. Can you really vent enough? So here was an incident that occurred in New York City. Rob Weedman was burned in this incident, as was firefighter Gersbach. And the fire started upstairs in the rear. The fire marshals from New York City said that it was a hair roller, curling iron that was left in a pile of clothes, started on fire. Mom had taken her children to school. She was gone on the order of 45 minutes. She comes back to her house. She hears the smoke. She's outside. She hears the smoke alarm going off from the outside. She makes entry in the front door, goes upstairs a little bit, sees smoke upstairs, and calls the fire department. Now again, some confusion. Where is she when she uses her cell phone and calls the fire department? She's in the structure. So the call goes out that someone's in the house. You know, you hear that, that sort of sets the tone. So what happens is the firefighters arrive and they do meet the resident outside. They go in to do a primary search. Ladder company gets on the roof and starts taking out skylights. So skylights are pretty easy to make a lot of ventilation pretty quick. And unbeknownst to the firefighters initially, the fire had vented the 2 windows out the rear already. So now we're picking up fresh air from the front stair, and the fire's venting out the rear. As the firefighters are doing their search in this room, they're getting hot, and the thought was we're going to vent to cool. So they start breaking windows. And once they break the first window and then the second window's broken, basically they flash over that room. Gersbach goes back into the structure. He's on fire. They have the line at the top of the stairs at that point. They hit him with water, cool him off, and he's basically treated and released that day. Firefighter Widman, who's seen here in the image, is coming out the window. And fortunately, the chauffeur was very quick to move the ladder to get him off. He comes outside on fire. Again, they hit him with a hose line to cool him off, and he was extremely burned, but fortunately he's alive. So basically what happens with the timeline here is that within the space of about a minute, they get over 40 square feet of vertical ventilation. Now, how many of you can do that with your saws, right? I mean, that's a lot of vertical ventilation. So if vertical ventilation were ever going to outrun the pace of the fire, I would think this would be the case. The problem is there's a lot of fuel in this row house. And the reason is the fire started back here. This is what they refer to as a railroad flat. These 4 rooms, coming from the rear bedroom to 2 middle bedrooms to the front bedroom, are basically connected with hardly any compartmentation. There are 2 wood frame glass doors between this room and this room. There's a hollow core door between this room and this room, and there's no doorway between this room and this room. The one skylight sits between these rooms. There's another skylight over the top of the stairs. There's a scuttle opening here, and there's another skylight over the bathroom. So all those skylights and scuttles were opened up pretty quickly. You can see that in the rear room, the fire had been burning for some time. It failed the gypsum board ceiling. It got up into the cockloft space, and it had heavily charred the wood joists that were supporting the roof. Again, the worst place to have fuel is in a place where it can't really burn very well. It just pyrolyzes and creates a tremendous amount of unburned fuel. So fuel at the ceiling, the hot gas layer is there. The hot gas layer is oxygen depleted already, and that's creating a lot of fuel to move elsewhere. Here's the front room where the firefighters sustained their injuries. Again, it went to a post-flashover condition, but as you can tell from the lath still being in place, not for a very long time. This is the stair where the line was brought up. And this window, again, you see we had bidirectional flow in the window. Hot gases out top, cool gases going in, which aided in Rob Weedman surviving. That the fresh air was coming in to cool him off. What little benefit that was, it was still some benefit. It helped. He got his face out the window, so his face piece remained pretty much intact with just some small damage to it. So again, we put in our model, we developed the timeline. Again, we're following from what we have from the Fireground radio and the radio traffic. So basically, before ventilation, we've got the fire here in the rear upstairs. After ventilation, you see that the smoke layer in the stairwell went up, but now we have flames at the ceiling, and we also have flames through all the bedrooms here as well. Showed that to the senior staff at FDNY. They asked us to run a number of cases where we would perhaps control the door, close the front door, or not take windows, or leave some of the vents in place. Anything we did to limit ventilation resulted in lower temperatures and less heat release rate. Slowed down the whole process. So heavy amount of fuel, ventilation couldn't get ahead of it. One of the reasons that the ventilation is hard to get ahead of, we close to 3? Oh, well, sorry. Break time.
All right, now we can start getting into the tactic stuff. So we laid a good foundation. Now we can start getting into some tactics, and then I'm going to try and breeze through this pretty quickly. Those of you that have been asking, what I'm going to do is we'll show you the UL website, ulfirefightersafety.com at the end. I'm going to go ahead and take this entire presentation, all the videos and everything, upload it on the Dropbox, and allow you to download it off a link off online. It might take a while to download. There's a ton of, it's gigs of stuff here, but we want to give it all to you so you can all use it. So I'm going to get through this quick so we can get Derek's piece about what they're doing to implement, which I think is the really important piece. So when it comes to ventilation, pretty much, why don't we have a good understanding of ventilation? And I think it becomes very obvious if you look at the tools that we have to train firefighters. So what we wind up doing is we get really good at the how, because that's what we can easily do in training. We can cut holes in roofs, we can force doors, we can break windows, we can do all the hows. You can't really easily simulate every other question, because what we have to work with, for the most part, is concrete training buildings and metal containers. So when you have this to work with, what did we learn this morning, right? You put some pallets in the corner of a concrete training building, you make a fuel-limited fire. When you have a fuel-limited fire, no matter where you vent, when you vent, or how much you vent, things get better. So we're showing our recruits in training that when I opened this up, things got better. Because we can't replicate reality, because we can't put realistic fuel loads in there, because we've proven that we can kill firefighters in training. And maybe we don't understand fire dynamics well enough to do that safely. So we have competing issues, right? We want to be able to show realistic conditions. However, we don't have the tools to do it. So we need something to kind of bridge the gap. And if you are using concrete training buildings, that's not to say that you can't teach good, effective, coordinated attack or ventilation tactics in these buildings. You can. It just takes good instructors to support it to make it work. So if you go ahead and you've got an instructor following the truck crew around, and they're being kicked in the butt, ventilate, 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 and they're not paying attention to where the hose line is, they're not paying attention to where they ventilate in coordination with the engine crew, the exercise needs to be interrupted and the proper teaching points need to be made because the fire is not going to respond in a negative way. You're not going to drive it to flash over on the truck crew searching ahead of the engine crew because you're burning 3 pallets in the corner of a concrete training building. Not to say that you would want to do that anyway, but how do you learn if all you see is everywhere I threw a metal shutter open had a positive impact? My visibility got better, the heat lifted. When I opened 2 windows, the heat lifted even more because we have a fuel-limited fire. So we need to be teaching better. So we ran a number of experiments to look at this exact issue. Here's an example of one of them. 1,200 square foot ranch house. We're going to look at the impact of opening the front door in a window near the seat of the fire. The purpose is to show you, during these experiments, we're looking at things that you can't normally look at. We've got views in every room. We've got sensors in every room. We've got the temperatures every foot in every room. We've got gas concentrations. We've got heat fluxes. We've got all kinds of measurements taking place in here where we can evaluate the tactics, in this case, open the front door and venting near the seat of the fire. And one of the things that I want you to see is the bedrooms remote from the seat of the fire are black. The fire sucks the oxygen out of those rooms. There's no air back there to burn. So even though there is plenty of fuel to burn, if there's no air to burn back there, it's not going to burn. It will burn where the oxygen is provided, which is going to be by the front door and by the front window. Another thing you need to notice is the bedrooms don't automatically have a giant lift of smoke when the front gets open, because the flow path is between the front of the house and the fire, not into the back of the house. You would have to vent the back of the house to get a tunnel or a small lift in the back that would ultimately spread the fire into the back bedroom. So we'll talk about a lot of that. Stages of fire development. Dan hit on this morning. We have to consider air into our stages of fire growth. And ultimately, this is pretty simple. We're going from ignition to growth. The fire runs out of air, starts to decay, our initial decay period. An opening gets made. Let's say the front door gets open. The fire responds to that oxygen and the fire takes off. All right, let's step it up a notch. 2 things are happening. The front door is getting open and a hole's getting put in the roof. That's what that looks like. The fire grows, it goes in additional decay. Front door gets open, provides air to see the fire, fire increases in size. But again, it hits a limit, right? It's only getting air through the front door. It wants to burn more than the air it's getting through the front door. But it's limited, it's fully developed. But then we go ahead and we open the roof. So now what are we doing? Well, we're allowing more air to come in through the front door, so our fully developed energy is actually higher. So now we've got fire coming out of the roof and fire coming out of the front door, and that fire still has more fuel. You make another opening, it's going to step up again until you interrupt it with water. And that's what's happening at the back end here. Hose line goes on the fire, we go into the decay stage, and we go ahead and put the fire out.
Steve, check your mic real quick.
So that's just 2 actions on the Fireground, or what the fire growth stages look like for opening the front door, opening the roof, and putting water on the fire. Had an incident in Prince George's County. Won't go into too much detail on this, short of saying small house, little to nothing showing, very small fuel load in the house, an issue with the hose line causing a delay. So what you're looking at is an engine company, a truck company showing up in very short order. Almost the exact thing that you would want, right? I got an engine crew, I got a truck crew coordinating. This can go well. Hose line had some issues. Truck crew got in ahead of the hose line. Wasn't communicated to the truck crew. The truck crew was forced to bail out, and you can see that the timeline of the first picture to the last picture was 2 minutes. What were we talking about earlier when we showed the experimental results as to what your coordination window was? From nothing, just about nothing showing, to fully involved front of the house, 2 minutes or less. Forcing the front door is ventilation. How many of you teach fire behavior with your forcible entry class? Probably not many, right? They're different subjects, so we tend to not put them together. Probably the best ventilation point you can make for any fire is a door. It goes all the way to the ground, allows for more air to entrain in, allows for some hot gases to go out the top. Quickest way to grow a fire is with a front door, or with any door for that matter. This just shows that simply opening the front door, whether it was the one-story house or the two-story house, didn't immediately make things better. Things got a heck of a lot worse. So that leads us to start talking about door control. If we can limit the air that's making it to the fire until we get water on it, then we're doing positive things. We're not allowing that fire to grow. Here's a short video that shows that not controlling that door until you have water ready to go will result in a bad outcome. The fire is not waiting for you. And there she goes. How many times do we see chief officers show up on the scene, get the front door open, or the occupants leave the front door open? And we assume that, man, they saved us the issue of forcing that front door. It's wide open already. We do our 360, and while we're doing that 360, that door's wide open, feeding air to that ventilation-limited fire, allowing it to increase in size. If you can limit that air, I'm not saying don't force the door and check for any occupants that might be inside the front door, but until you're ready to actually go and commence your attack on the fire, you need to limit that air. So we looked at the concept of door control. So we did 2 experiments side by side, where the first one, door all the way open, what we would normally do. Chock it open, it's all the way open, line goes through the front door. Second one, we opened it all the way to allow the crew to go in, and we simulated having a guy at the door hold the door closed as he's advancing line that closes the door about 2/3 of the way. So that line can run straight in. And again, there's all different variations of this and how you do it and everything else, and Derek's going to hit on some of that in a little bit. However, simple action of, say, closing that door halfway to limit the air can have huge impacts on how that fire grows and spreads. So here's the side-by-side. The one on the left was all the way open for 10 seconds, crew in, control the door. Second one, door completely open. What we're looking for is, how long does it take for the temperatures at 3 feet in the living room to hit 400 degrees? That's our comparison point, in which case we go ahead and we open a vent in the roof. You can see a pretty big difference between the two. If the fire doesn't have the air, it can't grow. Here's what it looks like. In the one-story house, it bought about 3 minutes before it hit that 400-degree mark. So if you want to talk about giving your crew more time to find the seat of the fire, and you're controlling the air, you're buying them more time of while they're operating in the flow path, because that's what's happening. The low pressure's behind you. The moment you go through that front door, you are between where that fire is and where that fire wants to go. So if you control the air behind you, you're lessening the chance that that fire's coming over top of you. In the 2-story house, because the fire was actually further from the front door, when we opened the front door, we were able to get that 400 degrees pretty quickly. When we controlled the front door, the fire almost put itself out. We had to open it all up to get the fire to come back. Because what happened was that air, the fresh air, wasn't making it all the way back to the fire. It was mixing with the smoke along the way, and 21% oxygen wasn't making it to where the fire was. So it took a lot longer for that fire to respond to the oxygen. And again, it's a temporary action. You want to limit the air until you gain the upper hand. And the upper hand is you begin to put water on the fire. The moment you begin to put water on the fire, open it all up. That's when your ventilation is starting to work for you. You're letting more out than the fresh air is allowing the fire to create. And it's not only for hose line advancement. I'm not advocating searching ahead of the hose line, but if there's a scenario where you need to do it, you can limit your exposure to being in the flow path by closing the door behind you. If you're worried about the door latching on you or you can't secure it and keep it from closing all the way, drop a tool in it or pick a different tactic. It's a tool in the toolbox. Rate of change. This one was significant, and we saw this repeatedly. From when you open the front door and begin your ventilation operation, whether it's front door and windows or front door and multiple windows, whatever it is, the reaction to oxygen is not instantaneous. There's a little bit of a delay. So in that little bit of a delay, I call it kind of the invitation period. Come on in. Things aren't that bad. You get a little tunnel of fresh air being pulled in. All right, this is the one I'm going ahead of the hose line. Well, when things started to go bad and got really bad, like 200 degrees to 2,000 degrees, was happening on the order of 10 to 15 seconds. So how quick can you run? That's what winds up happening. If you're not controlling the environment you're in with water or controlling the air, things can go bad in a hurry. This is why we see the YouTube videos of the firefighters on fire, because they were in the inlet. They were feeling pretty cool until that oxygen got mixed in there and everything lit up around them, and then it was bad quickly. So there aren't a boatload of warning signs. Venting near versus venting far. Here's another one. We always teach you vent near the seat of the fire. Why is that? Well, because it lets the bad stuff out quicker, right? The caveat that they forget to leave out, and then we commonly don't address in our training, venting near the seat of the fire is good if you're putting water on the fire. If you're not putting water on the fire, venting near the seat of the fire is the best way to make the fire the biggest, the fastest, because you're giving it the oxygen right where it wants it. So if you want to go ahead and take a fire that is ready to go to flashover and really make it flash quickly, give it air right near it. Or if you want to spread the fire to the other part of the building, go ahead and vent far. It's going to take longer for it to happen because you're going to have hot gases that are going to roll the ceiling, go to the low pressure that you created, right? Fire's a pump. It's creating a high pressure. Anywhere you create a low pressure to the outside, that's where those hot gases are going to go. So the hot gases are going to travel out the vent. As soon as the temperatures get hot enough in the room that they're leaving to ignite something in that room will quickly go to flashover. And then you successfully move the fire from one room to the other room. If you're putting water on the fire, venting near the fire is the best thing because you're taking the hot stuff, the high pressure stuff, moving it to a low pressure and getting it out of the house as quickly as possible, which makes your job easier. Reading smoke. Here's another one that maybe is not so obvious, right? So we get a fire inside a structure that's creating a high pressure, so it's pushing smoke out of every crack it can possibly push smoke out of to a point. And that point is when the fire runs out of air and begins to decay and the temperatures go down, the pressures in the structure actually go negative. So it might be 500 degrees inside that house. It's going to have a negative pressure because it's trying to suck oxygen from anywhere it possibly can. In the grand scheme of things, these are things that we would interpret as backdraft conditions, where you see some smoke pulsing in and out, and then all of a sudden, you've got nothing showing whatsoever. So the message here is, if you get on the scene and you've got nothing showing, don't get complacent. If you've got smoke in the area, you may have a fire that was in the growth stage, ran out of oxygen, went into the decay stage, and it's waiting to get opened up. And the moment it gets opened up, it's going to get the oxygen at once. And because of the timelines we're dealing with here, you're not going to get a backdraft. You're not going to get an explosion unless it's been burning for a really, really long time. But air's going to go in, fire's going to grow, it's going to go to flashover. Smoke tunneling, rapid air movement. You can learn a lot from the front door. If you force the front door and fresh air is pulling past you at about 12 to 15 miles an hour, you have a ventilation limited fire. That is not the one where you want to be getting ahead of the hose line. That's the one you want to control the front door on. The reason that air is moving so fast is because that fire is so starved for oxygen. Don't give it to it until you're ready to go with the hose line. The other thing you want to read from the front door, where's the smoke go? In this case, you get fresh air that tunnels in about the bottom third of the doorway. We call that the neutral plane as it cuts across the doorway. That is a really good sign that the fire is on the same level that you're on. You force that front door and you get smoke out top to bottom, and the smoke doesn't tunnel in through the bottom, fire's probably below you. You've got a basement fire. You force that front door open, you get lazy smoke, and the smoke starts to move towards the top of the door. The neutral plane is above the front door. You got a fire on the second floor. There's a lot you can learn by watching what the smoke is doing at that front door. And it's not magic. It's not something I made up. It's the pressure exchange that's happening at the front door because of the high pressure and the low pressure. Coordination. I'm not going to harp on this anymore. The important piece here is in our experiments in the 1- and 2-story house, with everything closed up, you were looking at 80 seconds in the 1-story and 160 seconds in the 2-story before things started to get really bad. If there's already a vent open and you pull up and you got fire showing out of a window, every subsequent vent that you make is going to respond that much faster. So your 80-second coordination window might be 30 seconds. So that's kind of your best case scenario with everything closed up. Chances are it's going to be a smaller window than that. VES, or as people bash me for, VEIS. Apparently putting an I in there ruined the fire service. My argument would be, well, let's take the E out because everybody knows if you vent, in order to search, you have to enter. I don't think everybody's teaching that you need to isolate that door. And I think putting the emphasis on that isolation is extremely important because if you don't isolate that door, you put yourself in the flow path. The problem is you put yourself in the opposite end of the flow path. So now even if you're a level above, like we show in this scenario, you're trying to crawl down the chimney. And I think we've got the video here that we showed this morning. How many people have a VES? How many people have a VES SOP? A lot of you should. There should be more hands because there's going to be the scenario where you show up and there's a credible rescue that needs to be made. There's a person right there in that window and your people need to know how to do that. They need to know. And one of the things that I see taught all the time that scares the heck out of me, people teach throwing the tip of the ladder through the window. And the problem I have with that is the moment the tip of that ladder goes through that window, the clock started. And that clock is how long you have to get that door shut before you made that room untenable for the person that's in there and any firefighter that's trying to enter into that window. If you don't have all your gear on, breathing air, ready to go through that window when you take it, you're not maximizing the amount of time you have to get that door shut. Look at the flow coming out of that window. If you're going in against that to get that door shut, you don't want to be giving up 30 seconds or a minute of your available time because you threw the ladder through the window, and then you got to put your mask on, and then you got to put your gloves on, and then you got to find your tool, and then you got to go up the ladder, and then you got to clear it out, and then you got to get in, and then you got to find the door. That takes a lot of time, and those of you that have practiced it know it takes a lot of time. You don't have a lot of time, so you need to maximize the time you have to get that door shut. This just shows the impact of closing that door. And you can see here that in the open bedroom, we take the ceiling temperatures from 450 to 150 immediately after shutting that door. The flow goes from 12 miles an hour to nothing. Dan talked earlier about convective flow. That 170 at the floor with a 12-mile-an-hour wind feels a hell of a lot worse than 170. But with 0 miles an hour and 120, you're now talking something that you can operate in. Best chance of victim survival and firefighter survival is behind a closed door. You could have, and Dan and I have seen this on many experiments, you can have the entire front half of a structure absolutely blowing fire. And if somebody's behind a closed door, let's say on the CD corner, there's a chance that there's a savable life inside that room. They put a closed door between them and the fire. Same thing happens if everything goes to crap on you guys and you find yourself having to bail out. One of the best things you can do to buy yourself time is to get a closed door between you and where the fire is. Takes you out of the flow path, allows the room that you're in to actually ventilate and allow the smoke to lift. And if you get to a window, you actually have time until that door burns through to have someone get a ladder to you and allow you to go out through that window. We've got a number of cases where firefighters have bailed out through windows on upper floors, and the thought of closing a door wasn't in their head. They're thinking, this is so bad, I got to get out that window. And I've never been in that situation, but I can imagine the last thing you're thinking of, unless you train on it, is getting a door shut. There's been cases where firefighters have waited for their comrades to jump out of the window while they sat there and cooked with the door 8 feet from them, and the thought process was not there to get that door shut to buy them a little bit of time. Vertical ventilation. We actually wrapped this series of experiments up. The online training program is finished, and we're going to release it next week. So keep an eye out on our website. There's going to be a new online training program that addresses the vertical ventilation stuff. And for anybody that thought, well, UL's going to tell us not to vertically vent anymore. UL's going to tell us that it's useless. No. That's not what we're telling you. What we're telling you is if you choose to vertically ventilate, here's what's going to happen. If you choose to do it this way, this is what you might see. Here's the timeline of which things happen. In this video, what we're showing is the impact of different hole sizes. And this is going to be pretty much the learnings out of this are no different than horizontal ventilation. I don't care how big of a hole you make. There's so much fuel, and it's so fuel rich, all you're going to do is make the fire bigger, unless you apply water or unless you control the air. So in the one on the left, we open a 4x4 hole, or 16 square feet. The one on the right, we open a 4x8 hole, or 32 square feet. What you're going to see is air comes in low. In one scenario, we get flames 15, 20 feet out of the roof. In the other scenario, we get 15, 20-foot flames out of the roof. And we get fire out the door. The fire is producing more energy than you can let out, even with a door and a large vertical vent. However, if you put water on the fire, a large vertical vent over the seat of the fire is the best low pressure you can create, and it allows hot stuff out quickly, allows everything else in the Fireground to be performed quickly. So if you understand what you're doing with your vertical vent, it can be a good tool. If you're just doing it because that's what you've always done, or we've always sent the truck to the roof, or we always cut a hole no matter what, you're missing the boat. You're not doing it right. And we want to be doing it right. So we get the fire burning to the front door. We've got the houses set up so that I've got pre-cut holes into the roof. Pay no attention to the guy falling on the ground. The cable got caught on the pulley, so he had to get the hole open. We also have a section of ceiling that's tied to a forklift. After we go ahead and pull the flap, simulating the hole being cut and pulled, we pull the forklift out of the way, and it pulls the ceiling out of the way, simulating a truck crew pushing down the ceiling on the inside. So we have a content fire here, not a structure fire. Ultimately, once you vent it through the attic, you create a structure fire. That's where the quick suppression becomes important. But really, what I want you to see is you don't get a lift. The fire doesn't pull up off the ground. It's a ventilation-limited fire that's looking for oxygen, and you're giving it more. You got 32 square feet of fire coming out of that roof, and you still got fire and smoke coming out of the front door. A little bit of water there is going to do a great amount of good, but ventilation alone, they can't just expand that hole in the roof, and all of a sudden, the conditions in the back bedrooms are going to get better. The back bedroom temperatures got much worse in both of those scenarios because we were increasing the burning. We did it on Governor's Island as well. We've got our townhouse, we've got a fire on the first floor. We're going to open up a 4x4 hole above the stairwell on the second floor. Watch the top right view in the living room once we open up the roof. So you got a fire that's pulling air through the front door back to the living room fire. Roof just got vented. Watch what's going to happen to that fire. It got bigger. The only place that vertical vent improved conditions in that structure was in like the first 4 feet inside the front door. Everything beyond that got hotter, burning increased, temperatures everywhere went higher. But you throw some water in through that front door, things get better. Operational time frame. Now we're going to start talking about some collapse and some basement stuff. We've run 20+ tests looking at floor collapses, all different kinds. Dimensional lumber, engineered I-joist with cutouts, hybrid trusses, steel seat joists, metal plate connected wood trusses, old houses, new houses, you name it. All of those dots right there are the shortest time to collapse, the longest time to collapse, and we've got your operational timeline layered over top of that. So with the exception of very few cases, all of those floors were collapsing mostly within the first 10 to 12 minutes of operations. So if collapse is not on your mind, when you're thinking operations in any structure, it should be, especially with engineered floor systems. Thermal imaging cameras, not an X-ray device. They're a surface temperature reading device. If you get onto the first floor and you think you're going to see that you have a fire below you simply by scanning the floor, unless there's a penetration between the basement and the first floor that hot gases are flowing through, like gaps in the baseboards or HVAC vents that burn through, your thermal imaging camera is going to tell you that it's 73 degrees on top of the carpet, even though it's 1,300+ degrees in the basement. Wood, carpet, hardwood, tile, all these things are very good insulators. They're very good at hiding heat signature. They're going to hide the signature from your thermal imaging camera. Here's an example that shows you there's a fire underneath this floor, and this is just a training exercise that got set up. He's going to go ahead and make a hole, and now you can see that there's high temperatures below that floor. You couldn't see it until he made that hole. And I'm not advocating that you take a pickhead axe and make a hole in front of you on every fire. Chances are you're not going to make it through the 1 inch of hardwood and the 1/2 inch OSB and everything else. However, you could see that you couldn't tell there was a fire there until the hot gases could travel through, and then you could see that there was a fire there. Size up is, we can't emphasize size up enough. First place to collapse was where it was getting the most ventilation. You would see that with a size up, understand what level the fire's on. We've got too many line of duty deaths where they didn't complete the 360, they didn't know what level the fire was on, and that changed the outcome. Ventilation and flow paths. If you're not going to die by falling through the floor, the next chance of dying is being in the flow path between the fire in the basement and the first floor. How many people have made it down the stairs into a basement fire and put a basement fire out? I would hope a lot of hands go up, right? We've been very successful doing that. But do you know why? Either the fire was small, it ran out of air so it wasn't that big, the basement wasn't ventilated, so it was kind of like holding your thumb on the end of the straw and didn't allow the flow to come up past you because there was no air low. These are important things. you might be a piece of glass or one door being forced away from being caught in a flow path between the basement and the first floor. We had a couple of brothers, Cherry Road in Washington, D.C., a couple of brothers, San Francisco, Diamond Heights fire, where they never opened up their hose lines. They got caught in the flow path above the fire or between where the fire was and where the fire wanted to go and got dropped and didn't get back up because a vent occurred on the floor below them while they were trying to find the basement stairs and make it down the basement stairs, and this is what the temperatures did. They went, in this scenario, they're going from about 250 to 1400 just by making some vents in the basement. And I think the common conception is, well, I'm going to let the hot stuff out of the basement, and if I let the hot stuff out of the basement, things are going to get better on the first floor. The opposite happens. Those basement stairs are the low pressure. That is the chimney. That's where the flow wants to go first. It doesn't want to go outside. It wants to go up and out through the front door. So if you give it that path, that's its primary path. You can't make enough openings in the basement to localize the fire in the basement. It wants to go up the interior paths. That's extremely important. You never want to have crews trying to make those basement stairs and make basement vents on them if the fire responds to the air and that's not well coordinated, they're probably not going to make it.
As the basement
Skip that one. Here's an example. Fire in the basement, flow path to the front door, and you all know how hard it can be to find basement stairwells in zero visibility with renovated houses. It's hard to coordinate those things. Just the hot gases following the flow path going to the low pressure. You saw it's venting out of the basement. That's not enough. It's not going to localize the fire. It takes over, goes up the stairs, up the first floor, or up through the vents, and flashes over the first floor. Here's the two fires I talked about, one in 1999, one in 2011. I'm not going to go into details, but there's been reports on both of them, and I suggest that you have a look at both those incidents. Well, let's talk about protecting the stairs. We're going to go ahead and we're going to flow 180 gallons a minute out of a 15/16" smooth bore at the top of the stairs. It's ideal. We're putting all 180 gallons into that stairwell. We are showering and creating a giant water curtain going down the stairs of this townhouse. You can see we're not having much impact on the basement fire that's ventilation limited and below there. We certainly didn't lift the smoke on the first floor. We're making a whole lot of steam. And I've had a few fire chiefs say this, and it's resonated with me pretty well. If you're not putting the fire out, you're not winning. So if that fire is burning unchecked in that basement, no matter what else you're doing in that structure, the structure's weakening. Even if the fire's not coming up the stairs, the fire's finding somewhere else to go. It's finding a low pressure into a wall cavity, into a vent. It's going somewhere. You could sit there all day and one of two things is going to happen. You're going to get cooked and steamed, or you're going to fall through the floor. So what's that look like? Well, you cool the temperatures at the top of the stairs from 600 to 400, and it's really about the victims, right? Or it's about the firefighters that you're protecting up the stairs. It went from 225 to 210 on the second floor. Is anybody going to notice a difference between 225 and 210 at the... No. And the important piece was to watch your back. In all these scenarios, the kitchen collapsed behind where the simulated hose crew would have been because the fire got up into the pipe chases, got up into the cabinets, ate away at the floor, caused a flashover in the kitchen, and collapsed the kitchen into the basement. Here's what that looks like. That's where the kitchen was. That's where the hose line had to go. So you actually have a low pressure behind you. if you're operating above a basement fire and you think the only place the fire is going to extend and harm the search crew is up through the basement stairs, I think you're fooling yourself. There's a number of avenues that fire can take. It could come up through a heat register underneath a sofa and flash a sofa over in a room that you can't see that's not right at the top of the stairs. And if you've got limited visibility because there is no neutral plane on the floor you're on, you probably have smoke to the floor, you may not see those things until it's too late. So if all your focus is on that doorway, you can get yourself into trouble, especially the longer you're there. If you're using floor sag as a collapse indicator, if the floor is sagging, clearly the structural stability of that floor is compromised. And what we saw was you may only have 5 to 10 inches of sag on a 20-foot span before the floor completely lets go. The problem is you only have a wingspan of about 3 feet when you're searching. So are you going to feel a difference of 2 to 3 inches between your right hand and your left hand? Maybe, maybe not. As you're working your way around furniture and things like that, you may not notice the sag before the floor completely lets go. So if you're using that as your barometer as to when it's time to get out, probably not a good, it's something to pay attention to, but it shouldn't be your sign that it's time to go. So what happens if we put water in the basement window? This is about the time that I had 10 FDNY chiefs crowded around me watching that thermal imaging view, waiting for a giant burst of heat and fire to come up those basement stairs. Because that's what we think, right? We think we're going to push the fire into the structure and up the stairs. So in this scenario, they flowed water longer than they probably needed to, but you can see that there's no giant heat push up through that interior stairwell. There wasn't a huge increase in flow coming out through the front door. And I think the reason for that is what we see in the temperatures. We always teach that water expands 1,700 to 1 and creates a lot of steam. The piece that we don't focus on too much is how much the gases contract when you take them from 1,700 to 300, 800 to 300, 1,200 to 400. That many hundred degrees of temperature drop will contract the gases. So you don't get a giant burst of steam and heat and smoke up to the second floor. And even if you did get some steam going up to the second floor, the temperatures look at the top of the stairs, 600 degrees to 200 degrees. So you're seeing a dramatic decrease in temperature. The bedroom on the second floor, remember before it went from 225 to 210? It went from 225 to 190. Now, because you have the upper hand, you can now vent that second floor and not have to worry about making it a low pressure and being in the chimney because you now have the upper hand. You can vent the heck out of that place because you have the upper hand. You're letting more out than that fire can create. So more operations can happen simultaneously because you have the upper hand. And another important piece of that is you flow water at that window, and you're flowing water at that window to knock the fire down, not to put it out. You got to get inside and finish it off. If you flow water for 15 seconds and you knock all the gases down and the fire goes back to the contents, and you just sit there and think you're done, the fire will come back. Because you're not putting water everywhere, stuff is still burning. So if you don't get inside and finish it off, it's going to come back. We did the same thing on the first floor. Fire in the kitchen. What would happen if as the truck crew is forcing entry into that front door, the engine crew gave the kitchen a shot for 20 seconds, 10 to 20 seconds off the ceiling before they went inside? Well, the traditional thought is, I'm going to push all the heat and hot gases into the structure downstream. And you got to remember, there's not a low pressure back there. So there is no flow path that those hot gases can go to. The low pressure is the kitchen window, which is why the fire's coming out that window in the first place. Here's what the temperatures look like. The kitchen dropped by 1,200 degrees. The middle room, which was also on fire, that's where the fire started, went from 600 to 300. And the rear room that had no fire in it went from 500 to 300. There wasn't a push, and that's 14 seconds of water. We're looking at those temperatures immediately at the end of that 14 seconds. Did we see a burst of heat go downstream? And we didn't see it. What if you softened the target on the second floor? What if you went ahead and hit it on the second floor before you went through the front door? Well, 3 feet off the floor in the hallway, using 25 gallons of water at a flashed over bedroom. Fire coming out of the bedroom, hallway door open from that bedroom. What if a victim was laying on the floor outside that bedroom? Well, that's what we looked at. 10 seconds of water, 25 gallons of water. Tight stream off the ceiling immediately where the water is needed, right in the compartment that's on fire. The fire doesn't know whether the water is coming from the interior door or coming from the exterior window. If it hits the ceiling and puts out the gases of what's flashed over, the low pressure can remain the low pressure. The window can still be the low pressure. Hallway temperatures drop from 273 to 104 in 10 seconds. If you did that and immediately followed it up by going inside and you trained on it and you could do it quickly, is that delaying the safety of the occupants inside the house? Something to think about. 4 points to consider. Just like any tactic, there is a right way and a wrong way to apply water from the outside depending on what you want to do. If you're going to open up a fog stream at a window that is a low pressure, the reason the fire is coming out is because that's the low pressure. If you open up a fog stream and you entrain a whole bunch of air with that water, heat and steam is going to move into the structure because you took away where it wanted to go. It's got to go somewhere, so it's going to mix in that room. If there is a vent open downstream, it is going to mix and it is going to move towards the vent that's downstream. If you keep a tight pattern with a straight stream or a smooth bore, and you don't whip it around in a circle, because if you whip it around in a circle, you might as well have a fog nozzle. The water breaks up and it looks just like a fog pattern. If you put it tight off the ceiling, knock the gases down, that window can still act as a vent because you're not sealing it off. That way, the hot gases can continue to come out the way they're going in. We do this on interior attack all the time. We have our O patterns and our clockwise and our counterclockwise and our T's and our inverted Z's and our upside down Australia pattern and stuff like that. What are we doing when we do that? Well, if you have a vent opposite the hose line, you actually move the steam ahead of yourself. You create a high pressure where you are and you push the steam to the low pressure. What happens if you don't have a vent opposite the hose line? Where's the low pressure? Behind you, right? So as you do this, that steam comes back over top of your head and goes back out the low pressure that you created. If you keep a tight pattern and move it ahead of yourself, you're creating less steam, less chance the steam's coming back over top of you. You're not as efficiently putting fire out because you're not putting water in as many places. But it's all about understanding whether or not you have a vent opposite you or you don't might change how you use your stream. It's not as simple as, I'm a fireman, I have water, I'm going to wet the crap out of everything. There's actually a reason that things happen on the Fireground. And if you can coordinate the vent opposite you, imagine I said coordinate there, like it's being made when you're ready for it to be made because it will make the fire bigger if you don't coordinate it. That doesn't mean the truck guy should screw the engine, I'm going to the back, I'm venting opposite the hose line. Well, if there's a 2-minute gap there, he may light up several rooms opposite of where the fire actually was. But if it's coordinated, the vent gets made, the engine crew moves in, and the steam all moves ahead of them, everybody's high-fiving each other afterwards because it worked the way it was supposed to. Same thing with exterior streams. If you cap the exit vent steam will move inside the structure because that's where you're forcing it to go. It's important that you understand that. The other thing was changing the flow path with air. We had a number of people that said, well, the line was moving through the front, I went into the back, I VES'd the back, and all of a sudden fire was coming over my head. It had to be because the line pushed the fire over me. Well, if you're in the flow path between where the fire is and where the fire wants to go, you shouldn't be surprised that you now have fire coming over your head. It goes both ways. If you come in and you make a vent point, hot gases are coming out over top of you. And if the hose crew does this as they move in, you're going to get steam that's going to move over the top of you because you're now in the exit point. So it's understanding the difference between how to make steam do what you want it to do and how to make it not do what you want it to do based on the scenario. And it's not simple as always do it this way. It depends on the timing and who's where. I'm going to pass it over to Dan for some townhouse fires.
Which we're going to go through very quickly.
Very quickly so Derek can do his implementation. Want that? And the mic. That would help.
I don't really need the mic, but the cameraman needs the mic, so. We will do that. We're all good? All right. Townhouse fires. Working with the city of Chicago. They had some townhouses, identical townhouses, 20 of them, in pretty good shape that they wanted to burn. So we started each of the fires in the sofa that you see, that nice blue sofa there in the front that was in the front living room. In the rear on the first floor, we had a dinette set, again, kitchen cabinets, more fuel there. Upstairs, we had the bedrooms furnished. We had two doors that were open to bedrooms, one, the bedroom in the rear at the top of the stairs, and the front bedroom that you see the red arrow to. And then the other bedroom had the door closed all the time up on the front. So each one of these, we went through and all we did was change ventilation, and then we hit the fire from the outside. So in this first case, everything's closed. We see the fire developing. We talk about the fire dynamics again. You know, the fire plume's coming up. The ceiling jet is going across the ceiling. You see the smoke spreading into the lower rear right corner there. That's the kitchen and the dining room. You see smoke coming up the stairs. The top middle image is the open bedroom at the top of the stairs. And then the top right image is the image that goes with the front bedroom. So right now there's no openings to the exterior. There's no bedroom windows open. The front door's not open. We see that the flames are starting to roll the ceiling in the first floor in the living room. You see we have smoke floor to ceiling in the bedrooms at a little over 3 minutes. Notice that what do you see from the outside? Because the heat is built up inside, the pressure is built up inside. For a little while there you saw smoke push around the edge of the door, and now you see nothing. Right? The pressure dropped. As Steve said, the smoke, the gases contracted. The officer opens the door a crack to take a peek. What happens? Fresh air goes in low, hot gas comes out high. You see what the flames are doing, right? The heat release rate is increasing again. Sorry. Now, because we let this drop pretty well and the fire was so fuel rich, this is going to take another 5 minutes or so before it actually leans out enough to get flames out the door and out the window. And we're going to get a little leakage at the window as well. But you see the fire's growing and responding. Conditions aren't getting any better in the house. We're actually starting to burn out the sofa, which was the original item of origin, so now the fire's spreading to other chairs in the room. We're starting to get some leakage at the picture window. Again, we're still floor to ceiling throughout the rest of the house in terms of smoke and oxygen-depleted smoke. And the only reason we're waiting for this one is so this will be your baseline, and you can see the differences as we start to open up more of the house on the subsequent tests. So we're starting to get a little more leakage out of the living room picture window. And now we're going to start to see flames appearing at the top of the door, and then followed by some flames out the edge of the window. And then we're going to hit it with a hose stream. So now the fire is starting to transition to flashover. So it took a long time. Because in effect, we had door control in place because the amount of fuel in there and the limited ventilation. So their initial hose stream, now they're introducing it in the house and starting to knock the fire down. So you see that we burned the sofa out completely. That's where we started the fire. Did these chairs, were they on fire back in the kitchen? No, they pyrolyzed. Oh, I like that. You guys are good. They pyrolyzed, right? They cooked off some fuel, but there was no oxygen back there for them to burn. If we wanted to get those chairs on fire, what do we need to do? Send a truck company around the rear and break the kitchen windows. No burning upstairs in the bedroom. We're not going to spend too much time on looking at the data here. Just this is the living room, this is the kitchen, the hallway, and the bedroom. The fire goes up at the ceiling. We're 1,500 degrees. 1 foot above the floor, we're over 400 degrees. Untenable there. The temperatures all drop down below 400 degrees. The front door is open. The temperatures jump back up to 1,500 degrees at the ceiling, 400 degrees at the floor until they increase a little further. We hit it with the line, drop them down. Similar pattern up and down throughout the house. The only difference is the magnitude. So in the front bedroom, we had temperatures at the ceiling at 600 degrees and 1 foot above the floor, only about 100 degrees. From temperature perspective, laying on the floor, laying on the bed, getting maybe survivable. But gas concentration, what do people typically die of in their home first? Right? Smoke inhalation, toxic gas throughout that house very quickly. So now in this case, same kind of deal. We light the fire in the same place. We're going to leave the door closed. And now when we open the front door, we're going to follow that very quickly with a firefighter with a pike pole taking out that front window. And watch how fast things transition. Again, the fire's building up. You see how rapidly smoke is filling the bedrooms upstairs. So we're 1:30 after a small flaming ignition on the sofa. Has anybody even called you yet? Not likely. Smoke down to the floor at the bedroom that's at the top of the stairs. 3 minutes. Watch this frame here. We have such a pressure differential that's what's going to happen here is the fire is trying to draw air. The gases are shrinking upstairs, so they're cooling off, and the pressure differential between the basement and the first floor is enough that it pulled the basement door open in front of our camera. So that pop that you saw was the basement door whipping in front of our camera. So the front door is open. It's 4 minutes, 30 seconds. They vented the window. You see how rapidly that transition's occurring because this is such a fuel-rich environment, it really wants a lot of air. Before, we were waiting for minutes before it transitioned to flashover. How long did it take here? About 30 seconds. Again, we're going to hit it from the outside. You see that we had more burning closer to the window this time. Again, up and down to 1,500 to 400. It goes down, open the door, break the windows. It rapidly increases up. Notice that the HS, the hose stream, when we're hitting it with the hose stream, we're not seeing any increase in the bedrooms or any push of heat or anything upstairs or other places in the house. This one's my favorite, so I'm going to show you just the one view first so you do the size up. In this case, this bedroom window is open. The front bedroom window is open. So now we made sure the fire's burning. We've closed the front door. And again, you know where the fire is. We lit the fire on the sofa. Again, a small flaming ignition. At 1:30, you're going to start to see some wisps of smoke coming out of that upstairs window. As the fire grows downstairs, the amount of smoke coming out that window, the top of the chimney, if you will, is going to increase. The temperature of the smoke is going to increase. The volume and the velocity of the smoke is going to increase. So at its peak, we're going to have smoke that's blowing out of that window horizontally almost 3 to 4 feet before it starts to go up. Notice what's happening at the doorway, right? High temperature in the living room, pressure building up in the doorway, forcing smoke around the edges of the door. And now watch it starting to puff, and then it stops, right? So the fire is losing energy downstairs. Now watch what happens up at the upper window. It's like somebody threw a switch. It's actually sucking back in the window right now. Watch when the first vent is made. Completes the flow path, right? We have bidirectional flow at the front door, hot gases out high, lower pressure fresh air down low, and a unidirectional vent at the top in the bedroom. About 80 seconds after they open that front door, the living room transitions to flashover. So, I mean, this is, again, one of those cases, as Steve indicated, sort of that invitation period. We got there, all we saw was smoke. We thought we had a chance to make a grab. We sent a crew in there ahead of the line. Where's your crew now? They either got to go out windows or run down through that fire. Again, knocking it down from the outside. I'm going to let you see the whole thing again, so now you can watch the smoke move upstairs. And what you're actually going to see as you watch this is, as it starts to darken down in the lower level, it's going to be picking up oxygen upstairs. The flame is going to move up the stairs, and then you'll see a glow and flames for a short period of time in the front bedroom before everything darkens down. So again, I think, the general public doesn't realize all the time how rapidly smoke spreads through a house when doors are open, or how rapidly this hazard builds. So you see the flames coming up in the bedroom. That's sort of when the push out the front windows at its peak. Now the flames are gone. The fire's darkening down throughout the structure. And we're going to see the smoke stop when it's actually pulling back in the window at this point. Opens the front door, you see that tunneling effect that was mentioned before, that fresh air, that gravity current being pulled in, that oxygen adding to the hot fuel and increasing the heat release rate. And then within that 80-second time period, transitioning the living room to flashover. Again, fuel in the kitchen, was it on fire? Nope, there's no oxygen back there. High pressure area with no oxygen. We can't push the fire with a hose line, and we can't get it to burn because there's no oxygen back there. Again, we have the up and down like we had before. Once again, notice when the hose stream goes in the door, even in the flow path here, all we see upstairs in that bedroom, that upper bedroom, is a decrease. We never see a spike of heat going up the stairs. This is at the bedroom window. We have temperatures up to 600 degrees going out of the window. Then they drop down. We open the door. They pick up again to about 500 degrees. Here's the velocity. The velocity out the window is about 12 miles per hour down here, and it's a little hard to see, but before we open the door, the velocity actually goes negative because it's sucking back in the window trying to get to the fire. Now we're going to switch gears and go to some single-family homes, wood frame construction, burns that were done with the Spartanburg Fire Department and ISFSI. So we're looking at size up. Size up is very, very important. So here they have a wood frame structure, about 1,000 square feet. We have the fire officer walking around with a video camera and a thermal imaging camera that are literally taped together and seeing what he can see in his 360. So the idea here is nothing's opened up. He's got smoke coming out of various locations in the house. They're going to go to the hot spot, vent the window, and introduce water in that window. So it's pretty clear to him here, where that energy is localized. So they're going to break the window, and ideally we'd flow water right away. But in this case, we're going to let it sit for a little bit so we can get a sense from the thermal imaging camera that the energy level is increasing in that room of origin as air gets in there. And then we're going to hit it with some water. Unfortunately, a very pathetic stream of water initially due to some hose kinks. But you'll see, even at that, it has a tremendous impact. So what's the impact there? Well, the first thing we're going to look at is just the impact of venting the window. So when we vent the window, you see that the temperatures in the living room go up a little bit. Temperatures in the rear bedroom back here aren't really affected. That's open there. The kitchen goes up a little bit. That's the next room adjacent to the fire room. And here we have this front bedroom with a closed door adjacent to the fire room, and conditions there are still tenable. Then we apply water through the window, and what happens in the front door in the front room? It goes from 700 degrees to 100 degrees near the ceiling, 200 degrees to 70 degrees at the floor. The rear bedroom, temperatures don't change much. Again, now's the time to vent those windows and let cool air in, or vent the front door, let some cool air in. The front bedroom has stayed tenable the whole time in terms of gas concentration and temperature. Now we're going to look at a different case. In this case, same kind of house, same kind of furniture, except we're going to have the front door open at different periods of time here. So you have the interior view, same scenario as we had in the previous fire. Again, hot gas layer is going to build up. The fire is going to darken down a little bit. You're going to start to see smoke pushing on the outside of the house. So look at the outside view. Think about size up. You know, what you're looking at from the outside versus what the conditions might be inside. This furniture was burning extremely fast. This was brand new furniture. We were worried the fuel literally wasn't going to last long enough. So what you're seeing, this glow here, is actually from a 500 watt halogen light in the corner. The fire's really darkened down pretty well. These are old homes, but in the fire rooms and adjacent rooms we installed new windows, thermal pane windows. These homes are built in the 1930s or so. So now we have the initial opening of the door. That helps the fire pick up. You see that it's starting to self-vent out of one of the windows. Vinyl frame, basically it's burning around the frame. We had hoped the door would stay open. That didn't work that time, so they're going to go back and open the door again and use a tool to keep it open. After they find the tool, yes. This bedroom here is the bedroom that's closed, so we're going to be checking the tenability in that bedroom. So now, interestingly enough, the heat flux in that bedroom is going up because we have the flames sweeping the porch in front of the window, adding some heat in there. Now they darken it down from the outside. So here's what it looks like, the impact of opening the front door. We certainly increased the temperatures in the living room from 1100 degrees to 1400 degrees. Temperatures in the kitchen increase. Rear bedroom doesn't change too much. The middle bedroom goes up a little bit. And then the front bedroom, you see the temperatures are increasing from 80 to 90 Fahrenheit. And we still have plenty of oxygen, no CO or CO2 to speak of, but the heat flux is going up a little bit. We also had thermocouples on the doorknob, because sometimes you want people, to be touching the doorknob and all that sort of thing. So the doorknob in the room went from 100 degrees Fahrenheit to 200 degrees Fahrenheit, and on the fire side it went from 700 F to 1200 F. Impact of water through the front door, dropping the temperatures throughout the space as you've seen before, and again the front bedroom, even though we had fire rolling the porch and everything, remains tenable. Show you one more scenario here. Again, size up, so you've got smoke showing. Where's the fire? The thermal imaging camera is going to help you here. It looks like you got some fire in the rear, or where's the fire? Fire's in the basement. This size up was a little slower maybe than we had hoped, but they were being very thorough. I'll just play it till they sort of get around the corner here. Oh, yeah. So the 360, again, extremely important to see what you have. I'm going to skip this for right now, but if you want a copy of this presentation, send me an email with your mailing address or give me a card and we'll make DVDs. We just sort of finished it this morning, getting all the best, latest stuff included, so, but we'll get copies out to you. Again, we attacked it from the rear on the level of the fire, so we weren't working over the fire, and it dropped temperatures significantly. We also had a simulated firefighter in there where we were looking at turnout gear temperatures and things like that. And now for the last segment, I'm going to turn it over to Derek, who's going to tell you how we put this in practice. Yes.
Now, I wanted to finish with my story of me attending that conference or the lecture at FDIC in the big lecture hall. So there was about 1,000 people. I was one of 1,000 students there sitting. Well, I had attended that session because I really did want to hear from the fire service leaders about what they thought of this new research that was out there. I had having prepared for this lecture, basically, reading through a lot of the documentation that Dan had published, as well as Steve. And I had numerous conversations with these guys as well before that FDIC in 2012. I had talked to Tim Marinar. I had talked to a bunch of people. You know, and I was trying to stay up on it because I'm part of the Fireground Survival Group. We want to make sure that all of this information is included within that curriculum. So as I was sitting there, and the conversation turned to the research that was being done and the negative vibe that was being put out there by the presenters, I was sitting there thinking, damn, are you serious? Like, have they not read the research? And I was starting to get a little agitated in my seat. Meanwhile, people all around me started cheering as if it was some sort of religious revival. So I'm sitting there thinking, did I come into the wrong church? I mean, this is odd to me. Am I missing something? Am I not reading the information correctly? That they all think it's a bunch of crap. But I'm sitting in the seat thinking, no, this is right on. This is what we need to know. This is science, and we need to apply it in the field. So I walked away from that lecture thinking, I bet you other folks within my own fire department feel the same way that they do. And if we are going to implement this within the Los Angeles County Fire Department, we are going to have to be very sensitive to these feelings, to this emotional topic. And it has to be, you know, nuanced in such that, it reaches people just in the right way. So the first thing we did is we knew that, see this thing right here? All those books. All of you have a stack of policies, procedures, and guidelines, right? And you're required to know all of those perfectly as you perform on every single emergency, right? Right. We all try to do that. It's impossible to remember all of that stuff. Well, it's also very difficult to include new information into our SOGs. Does it take a week for any of your organizations to do something like that? Heck no. Does it take a month? No way. Does it take 6 months? Maybe. Does it take a year? Probably, right? It takes a long time to make a change to policy, to manuals. And it's rightfully so. It's part of the bureaucracy. But nonetheless, we have to be a little quicker at getting information out there, especially as significant as this information is. This will change the way you do business in some of your fire departments. It did ours because we were very aggressive with vertical ventilation. And we never taught anybody to close the door or to limit ventilation. So what we have here are these manuals. They represent what we need to do on the fire ground. What you have on the right is information, how we wanted to present it to our population, our 3,000 firefighters, okay? But one of the things that we did was, the first thing we did was we brought all the training officers in. So those who were responsible for training our folks in Fireground survival? Or how about forcible entry? We have cadre groups that are dedicated to those disciplines. So Fireground survival, fire behavior, forcible entry, ventilation, those are the big ones right there. So that makes up, and also recruit training captains. That's about 100 folks in our fire department. We brought them all in and we said, hey, we got this new information to share with you. We want to make sure that you understand it, you digest it, but before you come, we need you to go through the online program that NIST put out on horizontal ventilation. UL. That UL put out on horizontal ventilation. You wanted me to put that plug in there, didn't you? Because you know it's being recorded. Sorry, NIST put something out good too. So anyway, they came prepared. And we also had them look over some NIST reports that dealt with overventilation of a structure and could have contributed to the fatality in these particular incidents. So they came prepared. We sat them down, went through all the information. We said, okay, this is the new program. We're going to it. And it was difficult for them to get on board. But they got on board. They totally understood it. And so we were ready then to throw it down to everybody in the county. Well, we have partners, okay? We have standards that we have to, or training standards that we have to abide by. And all those logos represent all the different organizations that have a play in our training. So there's a lot of them. And then what we did is we went back and we said, okay, we're going to identify all the different training topics that we need to train on in a calendar year. And we made this big list, and this big deal says, you know, this list goes on forever. There's probably, I don't know, well, it says 120 topics. That has grown to about 150 topics since that matrix has been created. So we wanted to identify all the different training topics that we need to train on in a calendar year. We also wanted to categorize them by their criticality rating, a scale of 1 to 3. So meaning, is it really critical or is it not as critical? This would fall in the categories of being extremely critical, which means we would have to review this stuff frequently. Okay? Let me go through a few of these here. What does that mean? Identify the minimum amount of hours for each topic. Then we looked at how often the topic should be covered, monthly. Yeah, so it could be once in a career, it could be annually, it could be semi-annually, it could be quarterly, it could be bi-monthly. So all those things, and then when should those topics be presented? And now when we were putting this together, some folks said, you're crazy. What is this going to do? How are you guys going to make sense of this? You're putting all this effort in just organizing a spreadsheet? I'll show you in a minute. Because this is our brain for our training right now. Based on delivery months, place an appropriate college semester. So now we connected with a college to help us do this in the end. All right, so once we got all that figured out, then we can look at making a standardized drill schedule for all 22 battalions, 3 shifts. So it's essentially 66 different battalions, all right? We wanted them to be consistent, to be training on all the same information, because we weren't doing that before. They would train on maybe one topic every month with limited content, but now training wanted to take control of the topics and also delivering each battalion certain content. And the reason we had to do that is because now we're going to be rolling out all of this information. All of this was created in knowing that we had a pretty big organizational change to handle. And knowing that I was sitting in the FDIC seat with all this emotion around me, which I'm trying to figure out, gosh, what is the best way to deliver this? So the first task was to organize the training program and to make them confident with what we're going to be putting out there. All right, so this right here was, let's see, that's June's drills. So you can see there was 3 drills there, and on there it says this is wet hose. So every month we have a wet hose, which means you have to go hands-on, go out there and actually pull your lines and flow water. But we wanted to have a specific objective in each one of these wet hose lays. It's now not the decision of the battalion chief or the captain to dictate what we're going to drill on. We're going to tell you what we want you to drill on. And we're going to give you some content to review before you go out there. All right, so for this particular one, we did attic fires, 3 hours. There's a hands-on prep. You'll notice we always use hands-on because we were going to move some of this stuff online, and firefighters don't like online, but they do. That's because what happens when you go into the station and you see them all kicking back, me included, I've been there, I'm guilty of it, and the phones come out and they're watching YouTube videos of fires, and they're looking at their Facebook or firefighters' Facebook and going to links, learning all kinds of stuff. So they're great online learners, but you just have to have very engaging content to make them interested. Would everybody agree to that? So we knew that. And we also wanted to drive them toward hands-on. We couldn't put online, well, we did at first, and it just created all kinds of a story. That simple word was like, you don't use the word. So everything matters. I tell Steve this all the time. Everything matters when you're training a firefighter. The images you put out there, the terms you use matter because they hang on the term. We all do it, not they, it's we. We're all part of this system. We're part of this culture that we've created. So it says hands-on prep, that's the online piece, and then hands-on, and it gives a drill code. It does an ISO requirement satisfied. We give them a little explanation there, and multi-company, station drill, and then we do say online at the far right, okay? They usually don't read that far anyway, right? So we're okay. All right, so identify the subject matter experts for the various topics. So every month we put out 3 to 4 of these drills. We have something to do with structure firefighting in the last 6 months worth of drills. And we need these SMEs to handle some of these other drills. We put out drills on thermal image cameras. We put on drills on wildland firefighting, radios, a variety of search and rescue, a variety of different topics. And so we go after SMEs who are in the field, and we get them to participate in creating this stuff. So our challenge here is, there's county right there, big red box, and here's our challenge. 58 cities we service, 2,300 square miles, 300,000 plus incidents, 3,000 firefighters, 170 stations. We go on about 2,000 structure fires a year, and we go on about 600 brush fires a year. The rest is, all the rest of the different types of incidents we go to. You can see our lovely freeways there. They're filled with traffic 24 hours a day, and these are our challenges. So when you have firefighters spread out over 170 stations, over 2,300 square miles, and you're trying to get out a consistent message, very challenging, especially when you're looking at organizational change. So we go to our college affiliation program partner, as well as our other partner, which is the California Firefighter Joint Apprenticeship Program, and we developed a system where we can deliver this stuff online through Blackboard and earn college credit for it. But first thing we need to do is make sure everybody has online access. Now that was a trick, and there's a whole lot of background stuff that I'm not going to go into that doesn't really, but it was political issues, there were bureaucratic issues that we had to fight through. But in the end, every firefighter in LA County now has internet access, and they can use the station computer to go on YouTube and all of that. So make drill content available via the web. The beauty of Blackboard is that we can post this information and they can get it from their phones. So now you have this stuff accessible 24 hours a day, 365 days a year, anywhere, anytime, off duty, on duty, doesn't matter. We can stream a video to you right now. I can upload it, have you watch it. I can find out if you watched it. I can test you on it, all of those things. So very powerful if you can get the message out like that. We felt like this type of message was so important, we were kind of staging for it. We were trying things out to make sure we had it just right. Now, if some of my county brothers and sisters are here, they'd probably go, well, you didn't get it just right, man. You still got to work on some stuff. But it's always a work in progress when you're working through these type of things. So we went out and got a, that's an intern right there. And this gentleman right here is a fire captain with us. The advantage we have in living in Los Angeles, we're near Hollywood. He's got a film background, graduate from LA Film School. He found out we were going to a lot of this video-driven stuff, and he raised his hand. He said, get me down there. I'm willing to help. I want to be involved. And so we had him. We had another guy who was a Hollywood producer who graduated UCLA, does some screenwriting and all that business. He's now a firefighter. He wanted to get involved. They're all involved. We'll take you too. Come on out, man. We'll make you a star. TSS website. So we needed to instill some confidence in our folks that we are capable of producing very high quality material, and we're going to get you good information that is consistent with the science out there. We're going to make sure this stuff is vetted and it's correct to the best we can based on our schedule. There are some limitations. The challenge with all of us in pushing things out to our various organizations is making it so it doesn't leave the organization liable for doing something wrong, right? So you want to make sure that you put something out that is correct and is consistent with the policy. Now, for this particular topic, we didn't have the time to create policy and procedures and guidelines. We're still working on that. Now, for recruit training, it's all implemented, it's all written. They are graded on door control. They're graded on all of this stuff that they talked about. And they can fail if they don't do it correctly. If they don't execute door control or ventilation correctly, they will be going down the hill. So we weren't able to adjust that fast to get everything into our manuals. So again, we were trying to create this atmosphere where our firefighters wanted to go and look at this stuff and had these inquisitive minds to engage once we pushed out the drill content. So the first thing we do is we host some teaser videos on our website. This is Training Services Section's website. Has anybody seen this before? No? Oh, one guy. Okay. It's not very popular, obviously, right? Because you can get this on the web. All right. So we had some fire behavior stuff. We did a bunch of drills. We took our film crew out there, shot some video, got people interested. They saw the video. Now there's a little bit of a buzz going on out there. We put a lot of people through fire behavior training. That's all great. You can see there's a reading smoke piece there. In fact, so this is one of the pieces, I think.
Hi, guys.
Okay. So
Hi, guys. Today
okay,
we're going to talk to you about forcible entry.
Yeah. So this is yeah, you're going to have to take it back anyway because it wasn't showing the video. So this is one of the pieces we created that went on here that talked about forcible entry. And, but like Steve said, when you're talking forcible entry or ventilation, you should be talking flow path, and you should be talking about controlling the door or the opening. Go for it.
All right, got to find my mouse here.
Nope.
Lost the mouse.
Want me to advance and...
Yeah, hang on a minute.
Man, I built you up right there.
Oh, we were right there.
Okay, let me keep talking.
Yeah, keep talking.
while
Let
you're,
me just
while you're
bounce
working
out
on
of this
that.
quick.
So anyway, the videos really, we're visual learners as firefighters. We're also tactile learners. So we want them to see something very visual, engage their mind a little bit, and we also read books about this kind of stuff just to make sure we were on track. So we were trying to sell a product to our firefighters, and it was almost like creating commercials and to get them to engage. All right.
Hi, guys. Today we're going to talk to you about forcible entry.
Hi guys, today we're going to talk to you about forcible entry. And this time not so much the how or what tool, but the why and what decisions you make, especially here where you're confronted with a man door and a roll-up door. Which door would you choose and why? This is the door we would choose to force entry. We would not choose a roll-up door. When you force the roll-up door, use a rotary saw. You now have an uncontrolled opening. There is a free flow of air to the seat of the fire, increasing the fire's intensity and the heat. We choose this door. We can leave a person here to tend the door, tend the line, and limit the amount of air into the seat of the fire. The person at this door can make sure line is able to go in and out, and also let you know where that door is. They can sound, they can flash their lights, they can bang a tool on the ground to let you know where the door is. The ability to control air to the seat of the fire is becoming critical, and by choosing this door, we can help do that. To check out more techniques on safe, effective, forcible entry, check out June's edition.
It's like a
Blackboard.
Bruce Lee movie.
Thanks again. Stay safe.
You can go to the next one.
I'm gonna let it play through just so it doesn't get unhappy.
Okay.
Then we'll-
Yeah. Maybe we'll just play it when we get to those slides. We can
There we
go right to your video. Do you have those on your desktop? Remember I unloaded those? We'll try it. We'll see what happens. Okay, so now we've got Blackboard and we've got these drills posted, all right? So we post these drills. So if I go to July drills, this is what showed up in July. So we had fire behavior, introduction, and flow path. So exactly what these gentlemen were talking about, it's posted. And we have video on there. In fact, we extracted when they were talking about flow path from the different lectures that they've given, and we've created our own chunk of flow path information video. And so the other thing we have in July, it was wet hose lay advancing an 1 3/4 line with door control. The door control was the different part. And we give them a little description. In fact, if I click the flow path one, you can see this is how a drill is lined up. You got a hands-on drill, introduction by FDNY Battalion Chief George Healy, does a great job there. The flow path video. You go to the wet hose lay. This is how it's organized. You click on those links. Let's go ahead and gives you a description on the hands-on drill. If I click on that link, this is what you see. You can print that out, go out in the drill ground, actually apply what you learned online. We go to the next one here. You click on that, and it gives you another video. So let's see if we can make this happen. Hopefully it will be loaded this time right. You have to wait until it shows up.
Yeah, I'm trying to, there we go.
Oh, there you go. By the way, I got a twin brother.
During
We're
the
all named
past several
same
years,
thing.
the Fire Service has benefited from NIST and UL's research on how fires develop in enclosed structures. They have taught us about how fast fires progress and how much energy is released when modern materials burn. We have learned the importance of controlling the fire by limiting the available oxygen. This research has resulted in significant changes to how we fight fires. Like many fire departments around the country, including FDNY, Los Angeles County Fire Department is changing how we approach enclosed structure fires to be consistent with this new research. All of these changes are to prevent flashover conditions from developing. We're changing a very old tradition of fire attack, where we don't flow water until at the seat of the fire. Now we are saying that it's okay to flow water above you into the smoke, which we know is fuel. This will cool the space around you. Also, by controlling the entry door, we limit the amount of fresh air that enters the building, thereby limiting the fire's growth. UL studies have shown this to be very effective in reducing temperatures and decreasing the potential of flashover. The first arriving engine to a structure fire has a lot of work to do in a short amount of time, especially if you're at scene with a 3-person crew. If you are arriving with a 4-person crew, one firefighter will be assigned door control, while the other firefighter and captain advance the line. As the door control firefighter, your job is to control the flow path of fresh air to the fire. You are trying to keep the fire ventilation limited or oxygen deprived. When the door control firefighter arrives at the entry point, the firefighter will assess the door. If the door is open, close it until the line is ready to be advanced. If the door is locked, force entry and control the access point. The firefighter assigned to door control establishes an equipment pool. This consists of a flashlight and irons, forcible entry tools. These tools are used to keep the fire attack team aware of their point of entry in the event of a rapid egress. You do this by placing the flashlight inside the door and using a tool to sound. After the fire attack team has entered the structure, the door control firefighter places the flashlight inside the door and then closes the entry door 2/3 of the way to control the flow path. If you are the door control firefighter,
So you get the idea. So we take them through the process. Now you got to apply it. That's the idea. Now I'm sure you look at it like, oh, did they take the, there's certain things you wouldn't do in your organization. That's fine. Create a video that includes all the things that you would do. We knew that it wasn't going to be perfect. And that's what I was saying before. It's difficult to be perfect. You can't. But you have to get out. You have to step out and go for it. And that's what we're saying is that we could have waited, but I didn't want to wait for someone to get hurt. When you're responsible for training, or if you're a local union leader or whatever, and you're responsible for the health and safety of these people, and the fire department isn't doing something, somebody has to do something to implement these tactics. You can't just wait on it. Because if you wait, if nobody writes anything, if nobody produces anything, somebody will get hurt. And it'll be our responsibility. We've learned about it. Now you have to implement it. All right, so let's move on. Wet hose lay advancing, we saw that. We also include a PowerPoint. And we have, the reason we do a video and a PowerPoint is because we want the individual to be able to download the PowerPoint, print it out, and also if they, we try to do highly visual PowerPoints. Everything is visual. And a nice thing about this is you can download it if you're in the doctor's office or something, you want to look through it, or if you're in the squad doing something but you don't have the ability to listen to a video, you look at the PowerPoint. So we even incorporated some of the things that are inside the Fireground survival program, where it talks about controlling the egress points, which you advance that a little bit forward and you control the door to control the flow path. It doesn't mention that in that program, but we're going to include that in the future editions. But nonetheless, it says, hey, put people at the entrance and egress points. Makes sense. We also, in our slide presentations, we reinforce, hey, you got to go try this stuff. You have to put your hands on the equipment to get comfortable with it. Controlling the door, it's a little more challenging than it looks. The hose got to be in a certain location. You got to put your body in a certain location. If I rolled the whole video, you would see we have the individual shift from the outside to the inside. And then they open the door when they start spraying water. All of those things are mentioned in that video. In fact, if you go to lacofdturnout.com, that video is posted on that website. That's our training website. You can grab that, use it as you wish. That drill plan is also there, as well as the PowerPoint. It's free for the taking. We figured other people would be interested. Go for it. You can use it. All right, so then we get back to August. This is our August drill, just so you can see. Now down at the bottom here, fire behavior, exterior water application, softening the target. This probably brings a tear to Steve's eye right here, because he loves to use that phrase, softening the target. So we click there. I'll just give you a little bit of a taste of this video. I know some guys are leaving, but I just want you to see what's up here.
We're waiting for it to, there we go.
Okay. Tell them they're welcome to come in and watch. Thanks for telling me.
Since launching Blackboard, our online training delivery system, Training Services section has posted several lessons dedicated to structure fire topics. The lessons have given us field personnel opportunities to discuss the science of fire behavior. Last month's drills included UL and NIST research on flow path and why controlling the door is so critical. Our battalion wet hose lays gave us a hands-on experience with these concepts. If you're like me, an individual assigned to the field, you're thinking, what will TSS post next? Is there more research showing how we should fight fire differently than how we previously trained? The answer to this question is yes. Let's discuss this structure fire. Fire showing from the front of.
So again, this was the follow-up to the previous month where we talked about flow path and door control. So we wanted to give them more information about exterior water application. That video goes through, it actually cuts pieces of what you just heard from Dan and Steve and includes it with one of our battalion chiefs who's got some street cred out in the field and who's been out there and done it. And actually, he goes, man, I've done things that were wrong, and so have I. So put me on camera. Let me tell the story. I've read the research. I think we need to be more aggressive at telling the story. And so that's what you see there. Again, you know, this is, we tweet our members about when we post something new on our training website so they can see what's out there. And obviously, we're going over. There's a lot of stuff to cover. We don't have enough time. We wish the class was longer. We appreciate you guys staying here. We'll stick around a little bit. If you have questions, please feel free to come up and throw them our way. Thank you.